When we look at the night sky, we see a universe that feels both familiar and incomprehensible. The planets trace their paths across the heavens, the stars shine from unfathomable distances, and everything appears bound together by an invisible hand. For most of human history, this mysterious binding was sensed but never explained. Why did the apple fall from the tree? Why did the moon circle the earth without flying off into the void? The ancients answered with myth, believing that gods or spirits pulled on objects and guided the stars. Yet slowly, through centuries of thought and experiment, humanity came to frame gravity not as myth, but as law. In the 17th century, Isaac Newton stepped into this mystery with a clarity that reshaped science forever. His law of universal gravitation declared that every mass in the universe attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. It was a bold, sweeping claim. Suddenly, the same rule explained both the falling apple and the orbit of the moon. Newton offered no machinery for how this force worked. Instead, he described it as instantaneous action at a distance, an invisible tether connecting two bodies across empty space. The simplicity was breathtaking. The accuracy was undeniable. But still, even Newton himself admitted unease. How could matter reach across emptiness to pull on matter elsewhere? The universe had been given a law, but it remained haunted by mystery. For more than 2 centuries, Newton's law held dominion. Engineers calculated trajectories, navigators steered ships across oceans, and astronomers mapped the orbits of planets with uncanny precision. The predictions were so successful that gravity came to feel like a known and conquered force. Yet in the 19th century, the cracks began to show. The orbit of Mercury deviated ever so slightly from Newton's predictions. The nature of light and electromagnetism was demanding a deeper framework. And then, in the early 20th century, Albert Einstein shattered the old picture with a new vision that was as radical as it was elegant. Einstein's general relativity declared that gravity is not a force at all. It is the curvature of space-time itself. Matter and energy bend the geometry of the universe, and objects simply follow the paths of least resistance within that curved geometry. A planet circling a star is not being tugged invisibly. It is rolling along the curved fabric of reality itself. Suddenly, the invisible tether was gone. Instead, space and time themselves were dynamic actors in the cosmic drama. What Newton had left mysterious, Einstein transformed into geometry. The prediction matched Mercury's orbit perfectly. The bending of starlight near the sun during an eclipse confirmed his bold claim. The universe was not governed by a force acting across emptiness, but by the very shape of space-time itself. This idea was more than mathematics. It was a transformation of reality. The image of the universe as a rigid stage where matter played out its dance gave way to a vision where the stage itself bends, ripples, and responds. Waves of gravity sweep through the cosmos when massive stars collide, carrying echoes of cataclysm across millions of light years. The presence of mass tells space how to curve, and curved space tells mass how to move. It is an elegant reciprocity, a profound marriage of matter and geometry. Einstein's theory is perhaps the most beautiful scientific insight ever conceived. And yet, the story of gravity remains unfinished. Even as relativity continues to pass every test, questions grow louder. For while gravity feels so familiar, it is also the strangest of all the forces. It is universal, affecting every particle of matter and energy. It is long-ranged, extending across cosmic distances. And it is incredibly weak compared to the other forces. A simple magnet can lift a nail against the entire pull of the Earth. Why is the most universal force also the weakest? Why does it refuse to be merged with the other forces that quantum physics describes so well? Gravity sits apart, familiar, yet alien, indispensable, yet incomplete. For centuries, It has been the force we thought we knew. But now, new voices whisper a startling possibility. What if gravity is not fundamental at all? What if it is not a basic ingredient of the universe, but an emergent phenomenon, a side effect of something deeper? Just as temperature arises from the collective motion of countless atoms, perhaps gravity arises from hidden microscopic laws we have yet to glimpse. Could gravity itself be an illusion born from information and entanglement at the most fundamental level of reality? If so, then the force that shapes galaxies and binds the cosmos is not what it seems. The apple falling from the tree, the moon circling the Earth, the stars drifting in their orbits, all may be the outward shadow of an invisible reality beneath. We thought we had conquered the mystery. We thought we had described it fully with laws and equations. But perhaps the most familiar force in the universe is only a veil, an echo, a mirage. If that is true, then everything we know about the cosmos may be poised for transformation. And so the story of gravity begins again, not as the force we thought we knew, but as the illusion that may conceal the true machinery of the universe. The universe has always invited us to believe in its solidity. We trust the ground beneath our feet, the constancy of the seasons, the sweep of the stars across the sky. To live in the world is to accept its permanence, and gravity feels like the foundation of that permanence. It keeps oceans from flying into space, holds the air we breathe close to the Earth, and binds the planets into their long celestial rhythms. It is so ordinary in our daily lives that it becomes invisible, a quiet presence we almost forget is there. Yet this quiet force is also the shaper of galaxies, the sculptor of cosmic structure, the reason stars ignite and worlds are born. We live in the arms of gravity, comforted by its familiarity, and rarely question what it truly is. Newton's triumph was to take this everyday experience and connect it with the grand motions of the cosmos. The same invisible tug that pulls a stone to the ground also binds the planets into their orbits. This unification of heaven and earth was breathtaking. For the first time, humans understood that the same mathematics governed both the fall of an apple and the trajectory of a comet. The cosmos was revealed not as two realms, one divine and one terrestrial, but as a single stage ruled by universal law. This insight reshaped philosophy, theology, and culture as much as it did science. The heavens were no longer ruled by mystery alone, but by equations that any mind could grasp. Still, Newton's formulation carried an unease. He had spoken of forces acting across emptiness, instantaneously, without medium. How did the Earth know the apple was there? How did the sun reach across 93 million miles to tether our world? Action at a distance felt magical, even to Newton. He admitted that the idea seemed absurd, but the mathematics worked. Generations of scientists accepted the strangeness because it gave them predictive power. Ships crossed oceans, telescopes tracked planets, and engineers built machines with confidence. But the unease never vanished. The universe seemed explained, yet it also seemed incomplete. When Einstein arrived centuries later, his revolution was as much philosophical as mathematical. Space and time were no longer silent stages. They were living participants. They could stretch, curve, ripple, and carry energy. The idea that the geometry of space-time could guide the paths of matter resolved the mystery of action at a distance. The apple falls not because the Earth reaches out with invisible fingers, but because the geometry of space-time directs its path. The planets orbit, not because they are tethered, but because they are gliding through valleys and slopes carved by the mass of the sun. The image is more intuitive, more elegant, more complete. The true test of any new theory is prediction. Einstein's general relativity predicted that light itself would bend when passing near massive bodies. In 1919, during a total eclipse of the sun, astronomers measured the positions of stars near the darkened sun's edge. The starlight had curved exactly as Einstein had calculated. Overnight, the quiet German physicist became an international figure, hailed as the mind who had rewritten the universe. Gravity was no longer a mysterious force acting across emptiness. It was the dance of geometry itself. This shift was profound not only for science, but for imagination. Gravity waves rippling across the cosmos became thinkable. Black holes, once considered absurd, became mathematical inevitabilities. The universe was stranger, more dynamic, more alive than anyone had guessed. And yet, as with Newton, triumph carried new puzzles. Relativity explains the grand motions of planets and the bending of starlight, but it struggles at the smallest scales. Quantum mechanics, which rules atoms and subatomic particles, does not fit neatly with the smooth curves of Einstein's space-time. The two pillars of modern physics refuse to merge into one seamless structure. Here lies the paradox of gravity. It is the most familiar force, woven into every heartbeat and every falling raindrop. Yet it is also the most elusive, the most difficult to reconcile with the other forces of nature. We can write equations to describe electromagnetism and the strong and weak nuclear interactions, but gravity sits apart, stubbornly resisting unification. The smallest grain of matter and the largest galaxy both bow to it, yet our theories fail when we try to describe them together. This tension hints at something profound. Perhaps our picture of gravity, even in its Einsteinian brilliance, is incomplete. Perhaps what we call gravity is not fundamental, but a reflection of something deeper. Imagine that beneath space-time itself lies a hidden structure, a network of information and entanglement. Imagine that the curves of geometry and the pull we call gravity are not primary, but emergent, like the warmth of a flame arising from countless molecules in motion. Could it be that the most familiar force is not a true force at all, but an echo of hidden laws beneath reality's surface? The suggestion is radical, but it is not unprecedented. Physics has taught us again and again that what appears fundamental may turn out to be emergent. Temperature emerges from microscopic motion. Pressure emerges from the collisions of countless atoms. Even solidity itself emerges from the repulsion of quantum fields. To propose that gravity emerges from deeper rules is audacious, but it follows a pattern. Nature often hides simplicity beneath complexity and reveals complexity from simplicity. The story of gravity, then, is not only the story of apples and planets, nor only the story of curved space-time. It may be the story of illusions, of shadows cast by unseen structures. And if gravity is an illusion, then the universe itself is stranger than even Einstein dared to imagine. The history of gravity is a story of confidence and doubt, of triumph and unease, of clarity always shadowed by mystery. Newton gave us a law that worked with astonishing precision, yet he left the mechanism unexplained. Einstein gave us a vision of curved space-time, a universe sculpted by geometry itself, yet his framework falters when pushed into the smallest realms of quantum physics. Each breakthrough brought us closer to truth, and yet each left the sense that gravity still hides something fundamental. The more we learn, the more it resists full comprehension. In daily life, we do not feel this tension. We walk, we fall, we throw a ball, and watch it arc through the air, all without questioning the hidden depths of the force beneath our feet. But in the vast scales of the cosmos and the minute scales of atoms, the strangeness becomes impossible to ignore. Black holes tear apart space-time, hiding their interiors behind event horizons. The early universe seethes with quantum fluctuations that later inflate into galaxies. When we attempt to describe these phenomena, relativity and quantum mechanics clash like oil and water. Equations diverge, infinities erupt, and predictions collapse into nonsense. This fracture is not a minor detail. It is the central puzzle of modern physics. For a century, scientists have pursued the dream of unification, the weaving of all forces into one coherent tapestry. The electromagnetic, strong and weak forces fit within the quantum framework, but gravity refuses to join them. It is as if the universe itself is split into two languages, one spoken by the very small, the other by the very large, with no translator between them. The consequence is profound. Without such a translator, we cannot fully describe black holes, the Big Bang, or the ultimate fate of the cosmos. Gravity is not merely a familiar force, it is a frontier of ignorance. And yet, there is something almost poetic about this frontier. For gravity is the most accessible of all phenomena. A child drops a stone and watches it fall. An apple tumbles from a tree. The tides rise and fall with the pull of the moon. Every living being has felt gravity since birth. To think that this universal experience may conceal secrets deeper than anything we have uncovered is both humbling and exhilarating. The force we thought we knew may be no force at all. It may be an emergent property, an echo of something more fundamental, perhaps rooted in information, in entanglement, in the very quantum fabric of reality. Imagine space-time itself not as a primary stage, but as a structure that crystallizes from unseen interactions. Imagine gravity not as a tug or a curve, but as a statistical effect of hidden data, the way temperature emerges from the jostling of molecules. This idea turns our assumptions upside down. It suggests that what we call reality may be built from information, and that gravity is the gentle whisper of this hidden order. It suggests that the cosmos we inhabit is not what it seems. If such a vision proves true, then the story of gravity is not one of completion, but of transformation. Newton and Einstein were not wrong. They were right within their domains, just as earlier thinkers were right in saying the stars move with purpose. But beyond every truth lies a deeper layer waiting to be uncovered. Perhaps gravity's true nature lies not in force or geometry, but in emergence, in the unseen patterns of a reality that is stranger and richer than we have dared to imagine. We thought gravity was the most familiar of companions. We trusted it as the bedrock of physics. Yet familiarity can be deceptive. The apple falling, the moon circling, the stars drifting in their courses may all be signs not of a fundamental force, but of something hidden, something waiting to be revealed. To recognize this possibility is to open the door to wonder once more. The universe has not finished surprising us. As we step forward into this new frontier, we leave behind the comfort of certainty. We embrace the possibility that what we thought was solid is in fact a shadow. The force we thought we knew may be the greatest illusion in science. And if gravity is an illusion, then reality itself may need to be rewritten. From the surface of the Earth, gravity feels simple. It pulls us downward, steady and constant, holding oceans in their basins and keeping the air wrapped around the planet. It seems unquestionable, the very definition of a force that never wavers. But when we stretch beyond the everyday and peer into the deepest mysteries of physics, gravity ceases to be simple. It becomes a puzzle, a misfit, a phenomenon that refuses to cooperate with the elegant frameworks that explain the rest of nature. The 20th century brought humanity two towering achievements of science. One was Einstein's general relativity, a theory of the large, describing the curvature of space-time and the motions of stars and galaxies. The other was quantum mechanics, a theory of the small, capturing the strange and probabilistic world of atoms, electrons, and photons. Each theory is stunningly successful in its own realm. Relativity explains black holes and gravitational waves. Quantum mechanics underlies every transistor, every laser, every medical scanner, and even the glow of your smartphone screen. Yet when we try to bring these two frameworks together, the harmony collapses. The mathematics rebels, predictions become nonsensical. This is the first great problem with gravity. It resists unification. Quantum mechanics tells us the universe is granular, built from discrete quanta, with uncertainty woven into its fabric. Relativity tells us space-time is smooth, a continuous geometry without breaks or pixels. The two visions contradict one another at their core. When we try to quantize gravity, to describe it in the same way as the other forces, the equations explode with infinities. Gravity simply refuses to be tamed by the quantum rules. Why does gravity not fit? One reason is its weakness. Among the four fundamental forces, gravity is the faintest whisper. The electromagnetic force is stronger by a factor of 10 to the power of 36. That means a small magnet in your hand can lift a nail against the pull of the entire Earth. The strong nuclear force binds protons and neutrons inside atomic nuclei, holding the very matter of existence together. The weak nuclear force governs radioactive decay and fuels the sun. All these forces operate with strengths that dwarf gravity. The universe is stitched together by interactions unimaginably stronger than the gentle tug we live under every day. This disparity is known as the hierarchy problem. Why is gravity so weak compared to the other forces? If all the forces arise from a common origin, as physicists believe they must, then why does one stand apart, orders of magnitude fainter than the rest? It is as though nature is whispering through gravity while shouting through the other forces. No one has yet answered this riddle. It may be a clue that gravity is not fundamental at all, but something emergent, something secondary. Or it may hint at hidden dimensions or unseen physics beyond our current grasp. The weakness of gravity also creates practical barriers. Because it is so faint, it is extraordinarily difficult to study at the quantum level. We can trap electrons, measure their spins, and detect the faintest quanta of light. But a single quantum of gravity, a graviton, has never been observed. If such a particle exists, it is beyond the reach of any experiment we can currently build. Even colliders smashing matter at nearly the speed of light cannot summon a graviton into visibility. Gravity, the most universal of forces, hides itself from direct detection more effectively than any other. As if this resistance to unification were not enough, gravity also confronts us with puzzles on the grandest scales. When astronomers measure the rotation of galaxies, they find that the stars move far faster than visible matter alone can explain. According to relativity, the gravity of all the stars and gas should be insufficient to hold the galaxies together. They should fly apart, yet they do not. Something unseen must be adding extra gravity. This missing ingredient has been named dark matter, a mysterious substance that outweighs all the visible stars and planets by a factor of 5. The problem deepens further when we look at the expansion of the universe itself. Observations show that the expansion is accelerating, as if some hidden energy were pushing galaxies apart with ever greater speed. This invisible energy is called dark energy, and it makes up about 70% of the total content of the cosmos. Add to that the 25% of dark matter, and we are left with a stunning conclusion. Everything we can see, from stars to planets to clouds of glowing gas, accounts for less than 5% of the universe. The rest is unknown, hidden, invisible. These puzzles reveal the second great problem with gravity. Its equations work beautifully, but only if we add vast amounts of unseen matter and energy. We do not know what dark matter is. We do not know what dark energy is. We only know that without them, gravity as we understand it does not match observation. For all its triumphs, Einstein's framework seems incomplete. The cosmos is whispering to us that something is missing, something we have yet to uncover. And so gravity, the force we thought we understood, becomes once again the most mysterious. It resists unification at the smallest scales. It demands invisible matter and energy at the largest scales. It stands at the center of puzzles that cut to the heart of physics and cosmology. Perhaps gravity is exactly as we think, and dark matter and dark energy are real, waiting to be discovered. Or perhaps gravity itself needs to be reimagined, redefined, rewritten from its foundations. The questions multiply. Why does gravity refuse to merge with quantum mechanics? Why is it so weak compared to the other forces? What are dark matter and dark energy, and why do they dominate the cosmos? These mysteries are not small details. They are cracks in the foundations of our understanding. They open the door to radical ideas, to bold new visions that challenge centuries of certainty. If gravity is not what we think, then the path ahead may lead to a revolution as profound as Newton or Einstein. The force we thought we knew may be an illusion born of deeper rules, rules that connect geometry, information, and quantum entanglement in ways we are only beginning to imagine. The problems with gravity are not obstacles. They are invitations to reimagine the universe itself. Gravity sits at the crossroads of triumph and crisis. It has carried us from Newton's falling apple to Einstein's curving space-time, from the orbits of planets to the detection of gravitational waves rippling through the cosmos. Yet with every victory it delivers, new puzzles emerge, and those puzzles grow sharper the deeper we look. At the smallest scales of the quantum world, gravity refuses to fit. At the largest scales of galaxies and cosmic expansion, gravity demands invisible partners we have never seen. These are not trivial inconveniences. They are profound signs that our understanding may be incomplete. The struggle to unify gravity with quantum mechanics is one of the deepest scars in physics. Quantum theory is not just successful, it is astonishingly precise. The magnetic moment of the electron has been measured and calculated to a precision of better than 1 part in a trillion, and the two numbers match. Relativity, likewise, is confirmed whenever we test it. GPS satellites would drift miles off course each day without correcting for relativistic time dilation. Both frameworks are tested, proven, and indispensable. Yet when they are brought together, their languages clash so violently that the mathematics disintegrates. Attempting to calculate the quantum fluctuations of space-time produces endless infinities, terms that spiral without limit, stripping the theory of meaning. It is as if nature is warning us that something in our assumptions is wrong. The hierarchy problem compounds the unease. Physicists dream of a grand unification, a single principle from which all forces and particles emerge. But gravity stands outside that dream, weak and aloof. It should be strongest at the tiny scales of the quantum world, but instead it fades to near irrelevance. A proton feels the pull of gravity a trillion times weaker than the push of the electromagnetic force. Why this enormous gulf? Some theories propose hidden dimensions that dilute gravity's strength. Others suggest that gravity leaks into realms beyond our perception. Yet none of these speculations has been proven. The weakness of gravity is not just an oddity, it may be the central clue to its true nature. On cosmic scales, the problems only deepen. The evidence for dark matter grows more undeniable with each observation. Galaxy clusters bend light from distant sources far more than visible matter can account for. Cosmic filaments stretch across the universe, their gravitational scaffolding demanding more mass than we can see. Precision maps of the cosmic microwave background reveal fluctuations shaped by the presence of unseen matter. Every line of evidence points to a hidden mass that outweighs stars by a factor of 5. Yet despite decades of searching, not a single particle of dark matter has been detected in a laboratory. Vast detectors buried underground wait in silence, listening for interactions that never arrive. Dark energy is even more baffling. The discovery in the 1990s that the universe's expansion is accelerating stunned the scientific world. Gravity should slow the expansion, yet instead it is speeding up. The simplest explanation is a cosmological constant, an energy inherent in empty space itself. But the value of this constant is bewildering. Quantum theory predicts a vacuum energy 120 orders of magnitude greater than what we observe. No other discrepancy in science is so extreme. If dark energy is not a cosmological constant, then what is it? A new field, a new interaction, something even stranger. The truth remains hidden. Together, these puzzles paint a troubling picture. Gravity works, but only with enormous patches stitched onto the fabric of theory. We add unseen dark matter to explain galaxies. We add dark energy to explain acceleration. We accept that gravity is weak for reasons we cannot fathom. We accept that it refuses to join the quantum world. It is as though the most familiar force is wearing a mask, hiding its true face behind layers of mystery. This situation cannot last forever. Physics thrives on unification, on stripping away the clutter to reveal the simplicity beneath. Newton unified the heavens and the earth. Maxwell unified electricity and magnetism. The dream now is to unify all forces into one, to see the universe not as a patchwork, but as a single tapestry woven from a common thread. Yet gravity resists. It may be that gravity is not fundamental in the way we assume. Perhaps it is not a force to be unified, but an emergent phenomenon that appears only at large scales, just as temperature appears only when we average over countless particles. If that is true, then our struggles are not failures, but hints. The incompatibility with quantum mechanics, the extreme weakness, the demand for invisible matter and energy may all be signs that we are misreading the nature of gravity. Perhaps we are like early natural philosophers, trying to explain heat without atoms, mistaking an emergent property for a fundamental force. If gravity emerges from something deeper, then the very puzzles that frustrate us become the clues that guide us. The problems with gravity are not just obstacles to be solved. They are cracks in the surface of understanding, cracks through which the light of a deeper truth may shine. To follow that light is to accept the possibility of radical change. To question whether the most universal force in nature is real in the way we think. To imagine that the familiar weight pulling at us every moment of our lives is not fundamental at all, but the whisper of a hidden order beneath reality. Gravity has always been the most paradoxical of companions. It is everywhere, yet elusive. It binds the cosmos together, yet slips through our attempts to fit it into a single theory. It feels inevitable, yet its properties are among the strangest of all. The problems it presents are not minor cracks, but deep fissures in the foundations of physics. Every time we look closer, gravity seems to be telling us that it is not what we think. Consider again its refusal to merge with quantum mechanics. At the Planck scale, where distances are unimaginably small, around 10 to the power of minus 35 meters, both quantum effects and gravitational curvature should be equally important. This is the realm where black holes evaporate into Hawking radiation, where space-time foam may churn with fluctuations, where the boundary between geometry and quantum fields should dissolve. Yet here, our equations collapse into chaos. Relativity speaks one language, quantum theory another, and neither can translate the other. String theory, loop quantum gravity, and other bold frameworks have tried to reconcile them, but no experiment has yet confirmed any of these ideas. We are left with a fracture at the heart of physics. The weakness of gravity magnifies the mystery. If it were merely another force on par with electromagnetism or the nuclear interactions, perhaps we could treat it within the same framework. But gravity is absurdly feeble. A single electron repels another electron far more strongly through electromagnetism than the Earth pulls on both combined. To explain such disparity, physicists have imagined scenarios where gravity seeps into extra dimensions, thinning out its influence in our familiar three. Others have proposed that what we perceive as weakness is actually a sign that gravity is not fundamental, but emergent, like the surface tension on water that arises only from the deeper interactions of molecules. The hierarchy problem is not just a nuisance, it may be the most important clue of all. Then there are the cosmic puzzles. Dark matter is required to explain why galaxies spin the way they do, why clusters of galaxies bend light more strongly than visible matter allows, why the universe's structure looks the way it does. But dark matter remains invisible, undetected by every experiment designed to capture it. Dark energy, even more dominant, accelerates the universe's expansion in defiance of intuition, yet its origin is unknown. These mysteries account for 95% of the cosmos. That leaves us with the sobering realization that all of human physics, all of our equations and theories, are built upon the small fraction we can see, while the overwhelming majority remains hidden. One way forward is to continue searching for these invisible ingredients. Perhaps new particles, beyond those catalogued in the Standard Model, lurk in the shadows. Perhaps new fields or exotic forms of energy will someday be revealed by clever experiments. Many physicists are confident that this will prove true, yet there is another possibility, more radical, more unsettling. Perhaps the missing pieces do not exist as separate entities. Perhaps they are symptoms of our misunderstanding of gravity itself. What if the equations we trust are incomplete? What if the geometry of space-time does not behave as Einstein described once we reach cosmic scales? What if the force we thought we knew is not a fundamental force at all? These questions lead naturally toward new visions, theories that dare to recast gravity as emergent rather than fundamental. Such ideas challenge centuries of certainty. But history teaches us that physics thrives on upheaval. When Newton reimagined motion, the old Aristotelian world crumbled. When Einstein redefined space and time, Newton's certainties gave way to deeper truths. Perhaps we stand at the edge of another such transformation, one in which gravity itself will be unmasked as an illusion. The problems with gravity, then, are not just failures of our current theories. They are the gateways to the next revolution. They force us to admit that the universe is stranger than we thought, that our most familiar companion may be hiding secrets beyond imagination. To face these problems is to acknowledge that physics is unfinished, that the story of gravity is still being written. And as we turn toward those who dare to imagine gravity as emergent, we glimpse the possibility that the very fabric of reality is built not from force and field, but from information, from entanglement, from patterns so deep they give rise to space-time itself. The cracks in gravity's facade may be showing us the architecture beneath. The mysteries are not the end of the story. They are the beginning of something new. The history of science is filled with moments when something that seemed fundamental revealed itself to be emergent. The heat of a flame feels like a basic property of matter, yet it is nothing more than the collective vibration of molecules. The pressure of a gas feels like a force in its own right, yet it emerges from countless collisions of invisible particles. Even solidity, the resistance of a table against your hand, is not fundamental but the product of electromagnetic interactions between atoms. What feels primary is often secondary. What feels basic is often an illusion born from deeper rules. In this light, a startling question arises. What if gravity, the most familiar of all forces, is not fundamental either? What if it is not a building block of the universe, but an emergent property, arising from deeper laws we have yet to glimpse? This idea is known as emergent gravity, and it dares to suggest that the pull that holds us to the Earth, that binds the Moon in orbit, that shapes galaxies, and governs the expansion of the cosmos may not be a true force at all. It may be a mirage, a large-scale effect of hidden structures beneath space-time. The analogy to thermodynamics is instructive. Imagine a room filled with air. For centuries, people believed heat and pressure were fundamental properties of matter, irreducible and primary. But with the rise of atomic theory, scientists realized that heat is simply the average motion of molecules, and pressure is simply the result of their countless collisions. These properties are real and measurable, yet they are not fundamental. They emerge from the collective behavior of deeper components. In the same way, emergent gravity suggests that the curvature of space-time and the force we call gravity may emerge from a hidden microscopic reality, one built not of fields and forces, but of information and entanglement. One of the boldest voices in this field is Erik Verlinde, a Dutch theoretical physicist who in 2010 proposed a radical reinterpretation of gravity. Verlinde argued that gravity is not a fundamental interaction, but an entropic force, a phenomenon that emerges from the statistical tendency of systems to increase in disorder. Just as a stretched rubber band snaps back because of entropy, not because of a fundamental force, Verlinde suggested that matter curves space-time because of underlying informational principles. Gravity, in this view, is the result of the universe's drive toward maximum entropy, a large-scale effect of microscopic information rearranging itself. This proposal was more than speculation. Verlinde showed that by treating gravity as emergent from entropy, One could reproduce Newton's law of gravitation and even Einstein's equations of general relativity. The familiar mathematics of falling apples and orbiting planets appeared as large-scale approximations of deeper statistical behavior. Gravity looked less like a primary actor and more like a side effect, a macroscopic mirage of microscopic rules. The idea gained momentum when connected to the holographic principle, a concept born from black hole physics and quantum information. The holographic principle suggests that the information content of a region of space is encoded not in its volume, but on its surface. Just as a hologram contains a three-dimensional image on a two-dimensional film, the universe may encode its information on boundaries. If this is true, then space-time itself may not be fundamental, but emergent from informational degrees of freedom. Gravity, in turn, would be the large-scale manifestation of how this information arranges itself. To imagine emergent gravity is to flip our assumptions inside out. We are used to thinking of space-time as the stage on which physics plays out, with gravity as the force sculpting its curves. Emergent gravity suggests that space-time itself is not the stage, but the performance. The stage is woven from information, and the geometry is an emergent pattern. Gravity is not the hand that shapes space-time, but the echo of deeper laws. Laws that may have more to do with bits of information than with mass and energy. This vision is radical, but it is also consistent with a broader theme in modern physics. Again and again, we discover that what seems solid is an approximation, that reality at its core is stranger and simpler than appearances. Light seemed continuous until we discovered photons. Matter seemed indivisible until we discovered quarks. Heat seemed fundamental until we discovered atoms. Gravity may be the next illusion to fall, revealed not as a force, but as a byproduct of deeper interactions we cannot yet directly see. The challenge, of course, is evidence. For an idea to move from speculation to science, it must make predictions and face the test of observation. Verlinder's proposal hints at new ways to explain galaxy rotation without invoking dark matter, new ways to understand cosmic acceleration without invoking dark energy. If true, emergent gravity would not only solve the puzzles of unification, but also rewrite our picture of the cosmos. It would say that the 95% of the universe we cannot see is not missing matter or energy at all, but the shadow of emergent laws misinterpreted as absence. To embrace such a possibility is to admit that the force we thought we knew, the one that has guided us for centuries, may not be a true force at all. It may be the most magnificent illusion in physics, an emergent effect born from the deep structure of reality. If that is true, then gravity is not merely strange. It is the greatest magician of all, hiding its true nature behind the veil of everyday experience, waiting for us to pierce the illusion and glimpse the hidden stage beneath. Gravity has always been presented as one of nature's cornerstones, a universal glue holding the cosmos together. But if the emergent picture is correct, then gravity is not a cornerstone at all. It is a structure built atop something deeper, a ripple upon a hidden sea. This idea unsettles the very foundations of physics because it suggests that the most familiar of all experiences, the weight that presses us into the earth, may not be part of nature's fundamental code. To understand how radical this is, consider again the analogy of temperature. For centuries, people treated heat as a substance. In the 18th century, scientists spoke of caloric, an invisible fluid that flowed from hot objects into cold ones. Heat seemed to behave like a real thing, and the caloric model worked well enough to make predictions. But the idea collapsed when atomic theory took root. Heat was revealed not as a fluid, but as the statistical motion of countless particles. Temperature is real, but it is not fundamental. It is an emergent property of microscopic motion. In the same way, emergent gravity suggests that what Newton and Einstein described so elegantly is not fundamental either. It is the macroscopic shadow of a deeper order. Eric Verlinder's proposal in 2010 gave this analogy mathematical teeth. He argued that gravity could be derived from the laws of thermodynamics applied to information stored on holographic screens, surfaces that encode the information of the space within them. By treating space-time as emergent from this encoded information, Verlinde was able to reproduce Newton's familiar inverse square law of gravitation. He even showed that Einstein's field equations of general relativity could arise naturally in this framework. What had once been taken as fundamental laws emerged instead as approximations of statistical behavior. But Verlinde did not stop there. In 2016, he expanded his proposal to tackle one of the great puzzles of modern cosmology: the rotation of galaxies. According to Newton and Einstein, galaxies should spin more slowly than they do unless they are embedded in vast halos of invisible dark matter. Verlinde suggested instead that the additional gravity we attribute to dark matter might be a natural consequence of emergent gravity. The entropy associated with dark energy, spread throughout spacetime, could lead to an additional force that alters galactic dynamics. In this way, emergent gravity offers not only a reinterpretation of the familiar, but also an explanation of the unknown. This vision ties deeply into the holographic principle, a concept born from the study of black holes. When matter falls into a black hole, the information it contains does not vanish, but is encoded on the event horizon, the surface boundary of the black hole. From this insight, physicists like Gerard T. Hooft and Leonard Susskind proposed that all the information in a region of space can be described by data encoded on its boundary. The universe, in a sense, may be holographic. Space-time itself may not be fundamental, but emergent from the entanglement of underlying quantum bits. If that is true, then gravity is not a basic interaction at all. It is a large-scale statistical effect, like the elasticity of a crystal lattice or the viscosity of a liquid. The power of this perspective lies not only in what it explains, but in how it reframes our questions. Instead of asking how mass curves space-time, we might ask how information arranges itself so that the emergent geometry appears curved. Instead of seeking gravitons, hypothetical particles of a fundamental gravitational field, we might seek the microscopic rules of entanglement that generate the illusion of a gravitational pull. The mystery of gravity becomes not one of force, but of information, not one of mass, but of entropy. Skeptics point out that emergent gravity remains a bold hypothesis rather than a proven theory. It must survive the scrutiny of observation and experiment, yet its appeal is undeniable, for it weaves together threads that have long dangled loose. The holographic principle, thermodynamics, quantum information, and the puzzles of dark matter and dark energy. It offers a picture of the universe in which space-time is not a given, but a construct, and gravity is not a master law, but an emergent whisper of hidden order. If this view is correct, then the cosmos is not built from space-time and matter in the way we imagine. Beneath those familiar elements lies a lattice of information, a web of entanglement, a structure we cannot yet see, but whose echoes we feel every moment we walk the earth or gaze at the stars. Gravity, in this vision, is not the skeleton of the universe, but its skin, an emergent layer concealing the bones of a deeper reality. The thought is dizzying, but it carries the thrill of possibility. Just as the discovery of atoms revealed heat to be emergent, just as the discovery of photons revealed light to be quantized, the discovery that gravity is emergent would transform our view of the universe. It would mark the next great shift in the story of physics, placing us once again on the edge of wonder. Gravity has always seemed like the ultimate anchor of reality. It grounds us, binds worlds, and sculpts the cosmic web. Yet the idea of emergent gravity insists that this anchor is not fundamental, but derivative, the result of patterns too subtle for our senses to grasp. To accept this is to change our relationship with reality itself. It is to imagine that what we feel as weight and what we see as curved space-time are illusions born from information, much as the warmth of sunlight is born from molecular vibrations. In this view, the true ingredients of the universe are not space-time and matter, but information and entanglement. Imagine that every region of the cosmos is encoded on its boundary, like a cosmic hologram. The bits of information on those surfaces interact, entangle, and organize themselves. Out of this hidden choreography, the smooth fabric of space-time emerges. Out of this emergent geometry, the phenomenon we call gravity appears. The bending of light near the sun, the orbit of planets, the fall of an apple, all arise from microscopic informational rules playing out on invisible screens. We are living inside a grand projection where what feels most real is actually emergent. This perspective does not diminish gravity. It elevates it into something even more mysterious. If gravity is emergent, then it is a signpost pointing beyond our current theories, a clue to the architecture beneath reality. Verlinder's vision is one attempt to follow that clue, but it is not the only one. Physicists exploring the connections between quantum information and space-time emergence, such as the work on the it-from-qubit hypothesis, are beginning to see the outlines of a world where geometry itself is woven from entanglement. In such a world, gravity is not an input, but an output, a large-scale effect of quantum data shaping itself into form. The implications stretch far. If gravity is emergent, then dark matter may not exist as invisible particles at all, but as the way emergent laws alter motion on galactic scales. Dark energy may not be a mysterious field, but a reflection of how information distributes itself across the cosmos. The puzzles that haunt cosmology may not require new ingredients, but a new perspective. Emergent gravity could dissolve mysteries by revealing that they were illusions created by our misunderstanding of space-time. Of course, bold ideas demand bold evidence. Emergent gravity has yet to stand the test of decisive experiments. Its predictions must be compared against the data with ruthless precision. Already, some results challenge its claims, while others hint at tantalizing agreement. The truth is not yet written. What matters is that the very possibility shifts the landscape of inquiry. It dares us to see gravity not as an immutable law, but as a phenomenon to be explained, like heat or pressure. It dares us to believe that the most universal force may not be a force at all. This shift in perspective recalls earlier revolutions. When Copernicus placed the sun at the center, he shattered centuries of certainty about Earth's place in the cosmos. When Newton unified the heavens and the earth, he dissolved the boundary between celestial and terrestrial motion. When Einstein revealed space-time as dynamic, he changed the very definition of reality. Each time, what seemed fundamental became emergent from something deeper. Emergent gravity may be the next step in this lineage, another turn of the cosmic kaleidoscope revealing a new pattern beneath the old. To walk under gravity's pull and imagine it as an illusion is to feel both wonder and vertigo. The force that has guided every step of your life may be nothing more than an echo of hidden order. The cosmos that seems so solid may be woven from information. The weight of your body, the orbit of the moon, the light bending around galaxies may all be shadows cast by a structure beyond our direct sight. Emergent gravity does not merely ask us to calculate differently. It asks us to see differently, to imagine the universe not as a stage, but as a projection, not as a given, but as a construct. If this vision proves true, then physics stands at the edge of another great transformation. The familiar story of gravity, from Newton's falling apple to Einstein's curved spacetime, will be joined by a third chapter, one in which gravity itself dissolves into emergence. We will realize that we have been living not under a fundamental force, but under the most convincing illusion in nature. And in recognizing the illusion, we may finally glimpse the deeper laws from which reality itself is woven. The more deeply we peer into the universe, the more we are drawn to a startling possibility. Gravity may not be about mass and force at all, but about information. In the last decades, a quiet revolution has rippled through physics, suggesting that reality itself might be built not from matter or energy, but from bits of information arranged in patterns we do not yet fully understand. If this is true, then gravity is not a fundamental force, but a statistical effect, an emergent whisper of the hidden informational architecture beneath space-time. The seeds of this vision were planted in the study of black holes. In the 1970s, Stephen Hawking showed that black holes are not entirely black. They radiate energy due to quantum effects near their event horizons, and over immense timescales, they can evaporate. This was shocking enough, but the deeper problem was one of information. If matter falls into a black hole and the black hole evaporates away, what happens to the information describing the particles that fell in? According to quantum mechanics, information can never be destroyed. Yet according to Hawking's calculation, it seemed to vanish. This paradox cut to the heart of physics. The resolution came from an unexpected angle. Jacob Bekenstein had earlier proposed that the entropy of a black hole, a measure of its information content, is proportional not to its volume, but to the area of its surface. Hawking's work confirmed this relation. The surface area of a black hole's horizon encodes the information of everything that has fallen within. This was the first clue to the holographic principle, the radical suggestion that the information describing a region of space is stored not inside it, but on its boundary. Just as a two-dimensional hologram can encode a three-dimensional image, the universe itself may be a kind of hologram. If information is stored on boundaries, then space-time itself may not be fundamental but emergent from these informational degrees of freedom. The geometry of space-time and the gravity that comes with it could be the statistical average of how this information arranges itself. Gravity, in this view, is not a basic force, but the thermodynamic behavior of hidden bits of data. It is no more fundamental than the warmth you feel from a fire, which arises from the microscopic jostling of atoms. This perspective is reinforced by the study of quantum entanglement, the eerie connection between particles that share information instantaneously across space. Recent research suggests that space-time itself may be woven from entanglement. Imagine a network of quantum bits, entangled in intricate patterns. The geometry of space-time could emerge from the structure of that network, with gravity arising as the large-scale statistical effect of how entanglement distributes itself. In this picture, without entanglement, space-time would dissolve. Gravity would not exist. Such a view transforms our understanding of the cosmos. The force that keeps our feet on the ground, that sculpts galaxies and bends light, is not a primary actor, but a byproduct of information. The universe is not built from space-time and matter, but from quantum data arranged into emergent patterns. Gravity is the shadow cast by this deeper order, a reflection of information flowing and entangling beneath the surface of reality. The beauty of this idea lies not only in its elegance, but in its power to explain puzzles. If gravity is emergent from information, then the mysteries of dark matter and dark energy may be reframed. They may not be substances or fields at all, but signs that our emergent description is incomplete. The anomalies in galactic rotation, the acceleration of cosmic expansion, could be the fingerprints of hidden informational laws we have yet to uncover. To see gravity as information is to see the universe as a computation, a vast quantum machine where bits of data evolve according to hidden rules. Matter, energy, and geometry are outputs, not inputs. The cosmos we observe is the emergent result of information processing on a scale beyond imagination. If this vision is true, then physics must be rewritten, not in terms of forces and fields, but in terms of entropy, entanglement, and information flow. This is not an easy shift to make. It demands that we abandon the comforting picture of space-time as a stage and gravity as a force, and replace it with the dizzying idea that both are emergent, like temperature or pressure, arising from hidden informational degrees of freedom. But history has taught us that the universe is rarely what it seems. Again and again, what we thought was fundamental has revealed itself as emergent. Gravity may be the latest and most profound example. If gravity is information, then our understanding of the cosmos is poised for transformation. The familiar pull we feel every moment of our lives may be nothing more than the echo of entangled bits whispering through space-time. The most universal force may be the most magnificent illusion of all. Gravity as information is more than an elegant metaphor. It is a framework that grows sharper with every insight from quantum physics and cosmology. To see why, we must return once more to the paradox of black holes. These objects are laboratories where relativity and quantum mechanics collide, and they expose the seams in our understanding with merciless clarity. According to Einstein's equations, a black hole is a region from which nothing can escape, not even light. According to quantum mechanics, however, information cannot vanish. The two statements clash violently when matter falls beyond the event horizon. Where does the information go? The holographic principle offers an answer. The information is not lost, but stored on the horizon itself, encoded in microscopic degrees of freedom that exist on the boundary. This principle has been made precise in the framework known as ADS-CFT, where a theory of gravity in a curved spacetime can be exactly equivalent to a quantum theory without gravity living on the boundary of that space. This duality is one of the most powerful insights in modern physics. It shows that gravity and spacetime can emerge from a purely quantum description on a lower dimensional surface. In other words, geometry and gravity may be nothing more than large-scale approximations of underlying information. From this perspective, the smooth curves of spacetime are like the smooth surface of a liquid. Dive deeper, and you find molecules in chaotic motion. In emergent gravity, those molecules are bits of information, qubits entangled across the cosmic web. The fabric of spacetime is woven from their correlations, and gravity is the statistical effect of how those correlations arrange themselves. Without them, the smooth geometry we take for granted would evaporate. This idea radically reshapes what we mean by reality. If spacetime and gravity are emergent, then the fundamental layer of the universe is not geometric, but informational. The true code of the cosmos is not written in distances and durations, but in entanglement and entropy. The curvature of space around the sun is not a fundamental law, but a macroscopic average, like the pressure in a balloon. The weight you feel as you sit in a chair is not the pull of a fundamental force, but the manifestation of hidden data aligning itself in ways we cannot yet see. The beauty of this vision lies in how it unifies concepts that once seemed unrelated. Thermodynamics, quantum mechanics, information theory, and general relativity come together under the banner of emergence. The entropy of black holes, the holographic storage of information, the entanglement that builds spacetime, all these threads weave into a single tapestry. Gravity is not an outsider force, but an emergent property of this tapestry, the natural result of how information organizes itself at the largest scales. If this is true, then the mysteries of dark matter and dark energy may take on new meaning. Instead of being exotic substances or fields, they may be the fingerprints of emergent information dynamics we have not yet fully described. The rotation curves of galaxies, the acceleration of the universe, could be signals not of missing matter or energy, but of our incomplete understanding of how information generates gravity. Emergent gravity thus holds the promise not only of unifying physics at the smallest scales, but of dissolving some of the greatest puzzles of cosmology. Yet, this possibility also challenges us. To embrace it, we must let go of the comforting idea that spacetime is fundamental. We must imagine instead a world built from information, where the geometry of space and the flow of time are byproducts, not bedrock. This requires not only new mathematics, but new imagination, the willingness to see reality as a projection, a hologram, a construct that emerges from hidden rules. The shock of such a view is profound. If gravity is information, then every moment you feel its pull is a reminder not of a force acting at a distance, but of a computation playing out in the invisible architecture beneath reality. Your weight is the echo of entropy. The orbit of planets is the geometry of entanglement. The universe itself is not a stage, but a story written in bits. We stand, then, on the threshold of a new paradigm. The old questions of how mass curves space-time and how objects fall may soon give way to new questions. How does information weave geometry? And how does entanglement give rise to gravity? If we can answer these, then we will not only have explained gravity, but have glimpsed the hidden machinery of the cosmos. To think of gravity as information is to step into a universe that no longer rests on the bedrock of space and time. Instead, it rests on patterns, correlations, and entanglements that underlie everything we see. The ordinary picture of reality, stars drifting in space-time, planets circling their suns, black holes lurking as abysses, is reinterpreted as a projection, a grand hologram woven from hidden bits of data. The pull that holds your body to the earth is not a force written into nature's foundation, but the large-scale whisper of information arranging itself into order. In this picture, the cosmos itself is a computation. Every atom, every photon, every grain of dust is a participant in a vast informational process. The geometry of space-time, the curvature that Einstein described, arises from the way entanglement patterns settle into equilibrium. Gravity is the statistical effect of entropy increasing, of information finding its natural arrangement. This is why Eric Verlinde compared gravity to an entropic force. Just as a stretched rubber band snaps back because entropy drives it to its most likely state, matter curves space-time because hidden information compels it to. The apple falls not because the earth pulls it, but because the underlying informational structure favors that outcome. This idea carries profound implications. If gravity is emergent from information, then the puzzles of dark matter and dark energy may be illusions born of our incomplete picture. When galaxies rotate faster than expected, perhaps it is not because invisible matter lurks in halos, but because the emergent informational rules produce extra gravity at large scales. When the universe expands ever faster, perhaps it is not because a mysterious energy fills the vacuum, but because the distribution of information across cosmic horizons compels space-time to accelerate. What we interpret as absence may be the shadow of laws we have not yet uncovered. The holographic principle strengthens this vision. It tells us that the information content of any region of space is proportional to its boundary area, not its volume. That is a radical statement. It means that a room filled with air contains no more fundamental information than the surface of its walls. The richness of the three-dimensional world we experience may be an emergent illusion, with the true description existing on a two-dimensional boundary. Space-time itself and the gravity within it may be nothing more than the unfolding of that holographic code. Quantum entanglement provides the stitching. Imagine countless qubits linked in patterns across boundaries. Their entanglement forms a web, and from this web, the geometry of space-time crystallizes. Distances, angles, and curves are not given in advance. They emerge from correlations among bits. Gravity is the curvature of this emergent geometry, a macroscopic echo of microscopic entanglement. In this way, the most universal force becomes not an actor, but a consequence, not a law, but a phenomenon of information. This shift in perspective is dizzying. It asks us to accept that the universe is not built from space and matter, but from information and entropy. It asks us to see our own lives, our weight, our movement, as emergent consequences of hidden data flows. Yet it also offers hope. By treating gravity as emergent, we may finally reconcile relativity and quantum mechanics, the two great but incompatible pillars of physics. We may discover that the unifying language is not geometry or probability, but information, a code that underlies both worlds. The consequences would ripple beyond science. If gravity and space-time are emergent, then reality itself is not what it seems. The solidity we trust, the the geometry we measure, the forces we feel may all be shadows cast by something deeper. To grasp this is to glimpse the architecture of the cosmos, not as a stage, but as a story written in hidden bits. To live under gravity is to live inside an illusion so perfect it shapes galaxies and births stars. And yet, illusions can be pierced. We are beginning to sense the outlines of the hidden order, to trace the threads of information that weave space-time. If we can decode them, if we can map how entanglement gives rise to geometry, then we will not only explain gravity, but also rewrite physics itself. The force we thought we knew will be revealed as the most magnificent illusion, and the universe will open itself to us in ways we can scarcely imagine. The night sky is a tapestry of light, but its motions conceal a troubling secret. When astronomers measure how galaxies spin, they discover that the stars move far faster than the visible mass can explain. According to Newton's law and Einstein's geometry, galaxies should tear themselves apart. The outer stars should fling away into intergalactic space, yet they remain bound, circling their galactic centers with quiet persistence. To reconcile this, scientists introduced a bold hypothesis. There must be unseen matter, invisible and non-luminous, outweighing the stars we see by a factor of 5. This hidden substance, called dark matter, became one of the great pillars of modern cosmology. For decades, the dark matter hypothesis has guided research. It explains the gravitational scaffolding of galaxy clusters. It fits with the patterns of cosmic microwave background radiation. It provides the invisible glue that builds the large-scale structure of the universe. Yet despite its success as a concept, dark matter itself remains stubbornly invisible. No particle has ever been detected. Vast detectors buried deep underground, designed to shield them from cosmic noise, have sat in silence for years. Particle accelerators have smashed matter at near light speeds, yet no hint of a dark particle has appeared. The universe seems to demand dark matter, yet it hides as if it does not exist. This absence has led some physicists to a radical possibility. What if the missing matter is not missing at all? What if the equations of gravity are incomplete, and the extra force we attribute to dark matter is not evidence of hidden particles, but of emergent laws we have not yet grasped? This is where Eric Verlinder's emergent gravity steps forward. In his 2016 proposal, he argued that the effects attributed to dark matter may arise naturally from the way gravity emerges from entropy and information. In this view, galaxies rotate as they do not because of invisible halos of particles, but because emergent gravity produces additional effects on large scales. To understand this, imagine space-time as a reservoir of information. Dark energy, the mysterious driver of cosmic acceleration, fills this reservoir with entropy. Verlinder suggested that the presence of this entropy alters the behavior of emergent gravity at galactic scales. The result is an additional apparent force that mimics the influence of dark matter. The extra gravity is not produced by hidden particles, but by the informational structure of space-time itself. In this way, emergent gravity could explain galactic rotation without invoking unseen mass. The appeal of this approach is clear. It dissolves one of the greatest mysteries of modern physics without introducing new substances. Instead of searching endlessly for invisible particles, we reinterpret the problem. The cosmos may not be filled with dark matter at all. The apparent need for it may be a sign that our description of gravity is incomplete. Just as Newton's laws failed to explain Mercury's orbit until Einstein provided a deeper framework, perhaps Einstein's equations fail to explain galaxies until emergent gravity provides the next step. Observations provide tantalizing hints. In some cases, Verlinder's equations match galactic rotation curves as well as, or even better than, models with dark matter. The theory predicts subtle deviations from Newtonian gravity that appear to align with data. If confirmed, this would mean that dark matter is not a substance but a mirage, an artifact of misinterpreting gravity. It would mean that the cosmos is not mostly invisible mass, but mostly emergent law. Yet the idea is controversial. Dark matter models have decades of observational success, and they explain not only galaxies, but the clustering of matter on cosmic scales, the formation of structures, and the precise peaks of cosmic microwave background radiation. Emergent gravity must match this success across all fronts, not just in galactic rotation curves. It is a tall order. Many physicists remain skeptical, pointing out that while emergent gravity can reproduce some effects, it struggles with others. The debate is fierce, for what is at stake is nothing less than our understanding of 95% of the universe. Still, the possibility cannot be ignored. If emergent gravity can explain the phenomena attributed to dark matter, then the cosmos we imagine may be profoundly wrong. The universe may not be filled with invisible particles after all. It may be governed by emergent rules of information and entropy that masquerade as missing matter. The dark halos that we have painted around galaxies may be illusions, shadows cast by the deeper architecture of space-time. The idea is daring, unsettling, and exhilarating. For decades, scientists have assumed that dark matter is real, waiting to be discovered. But perhaps it is not there at all. Perhaps we have been chasing a ghost, while the true answer lies not in hidden matter, but in hidden law. If so, then emergent gravity may be the key to solving one of astronomy's greatest puzzles. Galaxies are not the only arenas where the mystery of dark matter arises. The very scaffolding of the cosmos, the filaments that stretch between clusters, the halos that cradle galaxies, the webs that connect them, are all traced through gravitational effects that seem too strong for visible matter alone. In the standard picture, these structures form because dark matter provides the hidden bulk, creating wells of gravity into which ordinary matter falls, igniting stars and galaxies. This vision has dominated cosmology for decades, yet it rests on the assumption that dark matter is real, an assumption that remains unproven. Emergent gravity offers another possibility. In Eric Verlinder's framework, the key lies in the entropic nature of space-time. Space-time is not a fixed arena, but a dynamic medium that carries an intrinsic entropy, a measure of its information content. When matter is present, it displaces this entropy, altering the balance in ways that produce forces. These entropic effects grow more significant on cosmic scales, where dark energy also plays a role. The result is an additional component of gravity that manifests not locally, in the fall of an apple or the orbit of the moon, but in the vast sweeps of galaxies and clusters. In this way, the universe itself provides the extra gravity we have mistaken for invisible matter. The mathematics of Verlinder's model suggests that this emergent component arises naturally at the scales where dark matter is usually invoked. It produces extra attraction that grows with distance, explaining why stars at the edges of galaxies orbit faster than expected. It is not that hidden particles hold them in place, but that the entropic structure of space-time itself provides the missing pull. In principle, the same reasoning could extend to galaxy clusters, where gravitational lensing, the bending of light from distant galaxies, also points to unseen mass. Emergent gravity claims that this bending may be explained without invoking exotic particles, but as a property of information woven into space-time. This vision is powerful, but it faces challenges. The standard dark matter model not only explains galaxy rotation and lensing, it also fits the cosmic microwave background with exquisite accuracy. The delicate peaks and troughs of that ancient radiation are fingerprints of the universe's earliest moments, and they match the predictions of dark matter astonishingly well. Emergent gravity must account for this success without invoking dark matter, a formidable task. Some studies suggest that Verlinder's equations can mimic certain effects, but the full picture is still incomplete. Skeptics argue that while emergent gravity is intriguing, it cannot yet compete with the predictive power of the dark matter hypothesis. Yet history reminds us that anomalies can change everything. In Newton's time, the unexplained orbit of Mercury was treated as a nuisance until Einstein revealed it as a clue to curved space-time. Perhaps the rotation of galaxies and the acceleration of cosmic expansion are the same kind of clue. Signs that our picture of gravity is not complete. Dark matter may be an elegant patch, but patches can conceal deeper truths. Emergent gravity suggests that the missing mass may not be missing at all, but an echo of entropy shaping space-time on grand scales. If this is correct, then our image of the cosmos transforms. Instead of a universe filled mostly with invisible matter, we inhabit a universe where information and entropy drive the behavior of galaxies. Instead of unseen halos holding stars in place, emergent laws of gravity shape their motions. Instead of searching endlessly for particles that may not exist, we must turn to the hidden structure of space-time itself. The mystery of dark matter becomes not a question of missing mass, but of misunderstood law. This possibility ignites both hope and controversy. Hope, because it could solve a puzzle that has haunted astronomy for nearly a century. Controversy, because it challenges decades of research and billions invested in the search for dark matter. If emergent gravity is right, then entire generations of experiments have been chasing a ghost. The implications would ripple through physics and cosmology, forcing a rewrite of the standard model of the universe. The stakes could not be higher. At issue is not only the existence of dark matter, but the very nature of gravity itself. To test emergent gravity is to ask whether our most familiar force is real in the way we think. It is to risk overturning the foundations of modern cosmology. But it is also to embrace the possibility of a deeper truth, one in which gravity emerges not from mass, but from information, not from particles, but from entropy. And so the question hangs in the cosmic air. Could galaxies spin as they do without dark matter? Could clusters bend light without hidden mass? Could the scaffolding of the universe be built not from invisible matter, but from emergent gravity itself? The answer remains uncertain, but the pursuit of it promises to reshape our understanding of the cosmos. The search for dark matter has become one of the most ambitious quests in modern science. Across the world, vast detectors wait in silence, buried deep underground in mines or sunk beneath mountains to shield them from background radiation. These machines are designed to catch the faintest whispers of interaction between ordinary matter and hypothetical dark particles. Some theories propose weakly interacting massive particles, others suggest axions or sterile neutrinos. Decade after decade, experiment after experiment, the silence persists. Not a single particle of dark matter has been confirmed. In parallel, telescopes scan the skies, searching for indirect signs, gamma rays from annihilating dark particles, distortions in cosmic structures, subtle gravitational effects. Again, the signals remain elusive. The universe seems to demand dark matter when we interpret it through Einstein's equations, yet when we look for it directly, it refuses to appear. This tension is what makes emergent gravity so provocative. It asks a daring question: what if we are looking for something that is not there? In Verlinde's vision, the effects attributed to dark matter are not caused by hidden particles at all. They are the natural byproducts of emergent laws that govern space-time at large scales. Just as the pressure of a gas arises from countless collisions we cannot see, the extra gravity in galaxies arises from entropy woven into the fabric of the cosmos. If this is true, then the detectors will never find a particle, because there is none to find. The silence of the experiments would not be failure, but confirmation, the sound of an illusion dissolving. Such an idea is breathtaking, but it does not come without cost. The dark matter hypothesis, despite its invisibility, has been remarkably successful in explaining a wide range of phenomena. Emergent gravity must rise to the same standard. It must not only reproduce galaxy rotation curves, but also match gravitational lensing across clusters, explain the cosmic microwave background, and fit the evolution of large-scale structure. These are formidable challenges. Critics argue that Verlinde's equations may mimic some effects, but cannot yet account for all of them. Emergent gravity is a bold sketch, but the details remain unfinished. Still, even an unfinished idea can shift the landscape of thought. Emergent gravity reframes the puzzle of dark matter, transforming it from a hunt for invisible particles into a question about the nature of space-time itself. It suggests that the universe may be simpler than we think, not filled with exotic matter, but governed by emergent rules we have yet to fully grasp. It invites us to see galaxies not as mysteries demanding hidden mass, but as laboratories revealing the hidden architecture of information and entropy. The possibility is unsettling, for it threatens to overturn decades of work and billions invested in the dark matter paradigm. Yet science thrives on such upheavals. The orbit of Mercury once defied Newton's laws until Einstein revealed curved spacetime. The acceleration of the universe once seemed absurd until dark energy was proposed. Perhaps the strange motions of galaxies will one day be seen not as evidence for dark matter, but as the first clues to emergent gravity. If this vision proves true, the consequences will be profound. The cosmos will no longer be a dark universe dominated by unseen matter. It will be a luminous universe governed by emergent law, where information, entropy, and entanglement create the effects we mistake for hidden mass. Our picture of the universe will shift from one of invisible substance to one of hidden order. The missing matter will be revealed not in a particle, but in a principle. And so we face a choice of vision. Do we continue to search for the ghostly particles that have eluded us for nearly a century? Or do we dare to imagine that the force binding galaxies is not matter at all, but emergence? The answer will not come easily. It will require decades of observation, experiment, and debate. But the question itself is transformative. It forces us to look at gravity not as a settled law, but as a frontier, to see the cosmos not as a puzzle of missing mass, but as a mystery of deeper rules. In the end, the truth may not be dark matter or emergent gravity alone. It may be a synthesis we cannot yet see, a deeper framework that explains both. But the possibility that gravity itself could eliminate the need for dark matter reminds us of the most humbling lesson of science. The universe is rarely what we think. The familiar can dissolve into illusion. The invisible can prove to be unnecessary. And the greatest mysteries may turn out to be signposts pointing us toward truths more radical than we ever imagined. Every great idea in science must eventually step out of the realm of theory and face the crucible of observation. Equations alone cannot change our picture of the universe. They must be tested against reality, measured against the stars, weighed against the data. Emergent gravity, bold as it is, must stand before the same standard. If gravity is not fundamental, if it arises from entropy and information, then its predictions must leave traces in the cosmos. These traces must be seen, measured, and compared with the predictions of Einstein's relativity and the dark matter paradigm. Only then can we know whether emergent gravity is a vision of the future or a mirage of imagination. The most obvious place to test emergent gravity is in the behavior of galaxies. For decades, astronomers have measured the rotation curves of galaxies, finding that stars at the edges move far faster than visible matter allows. In the dark matter picture, these motions are explained by invisible halos of mass surrounding galaxies. In emergent gravity, they are explained by entropy woven into space-time itself. The two pictures make subtly different predictions. By comparing the details of rotation curves with Verlinde's equations, astronomers can test which framework matches reality. In some cases, emergent gravity reproduces the observed motions well, suggesting that its entropic effects may indeed account for the missing mass. But galaxies are only the beginning. Another powerful test comes from gravitational lensing, the bending of light by mass. Einstein's relativity predicts precisely how light should curve around massive objects, and observations of lensing have become one of the most powerful tools in cosmology. Dark matter models predict strong lensing effects, since invisible halos add mass to galaxies and clusters. Emergent gravity must reproduce these lensing patterns without invoking hidden particles. Some analyses suggest that Verlinder's model can account for lensing at galactic scales, but struggles at the level of clusters, where the evidence for dark matter is most dramatic. If emergent gravity is correct, then new refinements must explain this discrepancy, or else the theory risks collapse under the weight of observation. The cosmic microwave background provides yet another battlefield. This ancient radiation, released when the universe was only 380,000 years old, carries within it the imprints of density fluctuations and gravitational influences. The precise pattern of peaks and troughs in its spectrum matches the predictions of dark matter models with uncanny accuracy. Any alternative theory must reproduce this success. Emergent gravity has not yet been shown to fully account for the microwave background, though some suggest that it may offer different interpretations of its structure. To prove itself, emergent gravity must match this data point for point, or else concede defeat to the dark matter paradigm. Beyond these classic tests, there are new frontiers. Gravitational waves, ripples in space-time detected from colliding black holes and neutron stars, offer a new way to probe gravity's nature. So far, they match Einstein's predictions perfectly. If gravity is emergent, then at some level, deviations should appear, subtle differences in waveforms or propagation that reveal the hidden structure beneath. Future detectors may search for these clues, listening for whispers of emergence in the echoes of cosmic collisions. The stakes are immense. If emergent gravity passes these tests, it would not only replace the need for dark matter, but also signal a revolution in physics. It would show that space-time and gravity are emergent, that information and entropy lie at the heart of the cosmos. If it fails, then dark matter remains the stronger explanation, and the hunt for invisible particles must continue. Either outcome is profound. Science thrives on such tests. The orbit of Mercury revealed the cracks in Newton's laws and confirmed Einstein's vision. The bending of starlight during an eclipse proved relativity to the world. Now, the motions of galaxies, the lensing of light, the whispers of the microwave background, and the ripples of gravitational waves are the proving grounds for emergent gravity. The theory must not only be elegant, it must be true. To test emergent gravity is to confront the very nature of reality. It is to ask whether the weight you feel and the stars you see are the results of a fundamental force or the emergent shadow of hidden information. It is to risk overturning a century of cosmology, to wager that dark matter may be an illusion, and to trust that the universe will reveal its truth through the light of observation. The testing of emergent gravity unfolds across many scales of the universe, from the motions of stars within galaxies to the grand expansion of the cosmos itself. Each scale provides a new arena where predictions must meet observations, and each arena raises its own challenges. The beauty of science lies in this confrontation. For no matter how bold or elegant a theory may be, it is the universe itself that has the final word. On galactic scales, emergent gravity has shown early promise. When applied to the rotation curves of spiral galaxies, Verlinder's framework reproduces the observed motions without invoking halos of invisible matter. The entropic contribution to gravity grows stronger at larger distances, naturally explaining why stars at the edges orbit faster than Newton or Einstein would predict with visible matter alone. For astronomers, this is a tantalizing result. It suggests that perhaps the missing mass is not missing at all, but hidden in the emergent laws of space-time. Yet the match is not perfect. While many galaxies fit well, some outliers resist the equations, demanding refinements or exceptions that challenge the theory's universality. Clusters of galaxies raise even sharper questions. These vast structures, bound together by gravity, provide some of the clearest evidence for dark matter. Their gravitational lensing, how they bend and magnify the light of galaxies behind them, is stronger than visible matter can explain. In the dark matter model, the solution is simple. The clusters are wrapped in enormous halos of unseen particles. In emergent gravity, the explanation is more difficult. Verlinder's equations can account for some of the extra lensing, but not all. Observations, like the bullet cluster, where two galaxy clusters have collided and left visible matter separated from the bulk of the gravitational lensing signal, appear particularly challenging. For many physicists, such data stand as powerful arguments for dark matter. If emergent gravity is to succeed, it must explain these phenomena with equal clarity. The cosmic microwave background remains an even greater challenge. The detailed structure of this ancient radiation matches the predictions of a universe filled with dark matter and dark energy with remarkable precision. The positions and amplitudes of its peaks are fingerprints of how matter and radiation interacted in the early universe, and dark matter plays a critical role in shaping them. Emergent gravity has not yet provided a full account of this structure, while some researchers suggest that alternative information-based models could reproduce similar effects. The evidence remains heavily weighted toward the dark matter paradigm. Here, emergent gravity faces its toughest trial, yet science is not only about defending old frameworks, it is also about pushing new ones to their limits. Gravitational wave astronomy is a young field, and it may yet provide tests that distinguish between fundamental and emergent gravity. So far, the waves detected from colliding black holes and neutron stars match Einstein's predictions with uncanny precision. But emergent gravity suggests that at very subtle levels, deviations may exist, perhaps in how waves propagate over cosmic distances, or in how they interact with the entropic structure of space-time. Future observatories, more sensitive than today's instruments, may be able to detect such differences. A tiny anomaly in a waveform could reveal the fingerprints of emergence. The expansion of the universe also offers a testing ground. Dark energy, invoked to explain cosmic acceleration, may itself be a manifestation of emergent gravity. Verlinder's model suggests that entropy associated with the cosmological horizon creates an additional force that drives expansion. If this is correct, then the rate of acceleration, its changes over time, and its imprint on the distribution of galaxies should all carry signs of emergent law. Ongoing and future surveys of large-scale structure may provide the data needed to confirm or refute this possibility. Testing emergent gravity is not simply about confirming or denying a single theory. It is about probing the limits of our understanding. If the theory fails, it will still teach us, for every failure sharpens the contours of truth. If it succeeds, it will reshape physics at its core. Either way, the process is invaluable. The universe demands that we test, that we measure, that we question, and in doing so, it leads us closer to the hidden architecture of reality. In the end, the testing of emergent gravity is the testing of our imagination. It is a reminder that science is not a closed book, but an unfolding story, written line by line in the light of stars and the ripples of space-time. Whether emergent gravity proves true or not, its confrontation with data is a necessary step in the journey. For only by daring to imagine that gravity itself might be an illusion can we ever hope to uncover the deeper truths that lie beyond. The fate of emergent gravity rests on the sharp edge of observation. The theory is young, bold, and incomplete, but its confrontation with data will decide its future. Every experiment, every telescope, every detector becomes a stage where the universe itself offers its verdict. Some verdicts so far are encouraging, others are troubling. Together they form a dialogue between imagination and reality, a dialogue that defines the very essence of science. Consider again gravitational lensing. When light from a distant galaxy bends around a foreground mass, it carries with it a message about the distribution of gravity. In simple cases, such as individual galaxies, emergent gravity's predictions line up reasonably well with observation. But in clusters, where visible matter separates cleanly from the lensing signal, as in the famous bullet cluster, the story becomes more complicated. The lensing maps suggest mass in regions where little visible matter exists. Dark matter explains this easily. Emergent gravity struggles, for it must account for the same effect without hidden particles. Critics argue that these systems are a death blow to emergent gravity. Supporters reply that the theory is still developing, and refinements may yet rise to meet the challenge. The same tension appears in cosmology at large. The standard model of cosmology, with its mixture of dark matter and dark energy, fits the cosmic microwave background, galaxy clustering, and expansion history with breathtaking precision. Emergent gravity has not yet matched this success, but it is worth remembering that Einstein's relativity, when first proposed, also failed to explain all known data. It required years of refinement, testing, and new insights before it stood firm. Perhaps emergent gravity is in the same stage, incomplete but promising, awaiting the tools that will sharpen it into clarity. The most exciting opportunities may lie ahead in the new era of observation. Gravitational wave astronomy, still in its infancy, offers a way to probe the deep structure of space-time. If gravity is emergent, then ripples in the fabric of reality may reveal subtle signatures of the hidden information beneath. The speed, dispersion, or polarization of gravitational waves may someday betray the fingerprints of emergence. Similarly, surveys of large-scale structure, the cosmic web of galaxies stretching across billions of light-years, may uncover patterns inconsistent with dark matter, but natural in an emergent framework. To test emergent gravity is to balance between risk and reward. If it fails, it will still have pushed us toward deeper questions, challenging the complacency of assuming that dark matter must exist simply because it is convenient. If it succeeds, it will rewrite physics, dissolving one of the greatest mysteries of science and revealing a universe governed not by hidden particles, but by hidden principles. In either case, the pursuit is worth the struggle, for it forces us to test the limits of what we know. What matters most is that emergent gravity is not just a speculation, but a theory daring to make contact with data. It has predictions, however tentative, and those predictions can be tested. That is the mark of science. The universe does not bend to our preferences. It demands evidence. If emergent gravity survives, it will be because the cosmos itself affirms it through the motions of stars, the bending of light, the whisper of ancient radiation, and the echoes of colliding black holes. If it fails, it will fall as countless theories have before, honored not for its survival, but for the clarity it brought to our questions. The testing of emergent gravity is therefore not just about gravity. It is about the scientific spirit, the courage to risk error in the hope of deeper truth. We test because we must. We test because the universe is vast and mysterious, and our theories are only guesses until confirmed by observation. Whether emergent gravity proves true or not, the act of testing it brings us closer to understanding the cosmos. It reminds us that even the most familiar force may conceal secrets, and that the path to truth is written not in certainty, but in the light of evidence. And so, the battlefield of observation awaits. Galaxies, clusters, radiation, and waves, all are voices in the cosmic choir, ready to sing the truth of gravity. The question is whether we are listening closely enough to hear. The quest to understand gravity has always drawn us toward the very edge of the possible. Newton revealed its universality. Einstein revealed its geometry. Verlinde and others suggest its emergence. But behind all these visions lies a deeper question. What is gravity's true connection to the quantum world? For a century, relativity and quantum mechanics have stood as rival descriptions, each brilliant in its domain, yet unable to merge into one. The smooth curves of space-time resist the grainy uncertainties of quanta. The clash between them defines the central riddle of modern physics. Emergent gravity dares to answer by turning the question inside out. It suggests that the connection between gravity and quantum theory is not forced, but natural, because gravity itself may be born from quantum entanglement. Quantum entanglement is one of the strangest features of the microscopic world. Two particles prepared in a shared state remain linked no matter how far they travel. Measure one, and the other responds instantly, as if distance does not exist. Einstein called it spooky action at a distance, yet experiments confirm it again and again. Entanglement is not an illusion, but a fundamental feature of reality. What if space-time itself is woven from these links? What if distance, geometry, and gravity are all emergent properties of entangled quantum bits? This idea is captured in the phrase, "it from qubit," a playful echo of John Wheeler's famous slogan, "it from bit." Wheeler had suggested that information lies at the root of physical reality, that every particle, field, and space-time point ultimately derives from binary choices, yes or no, 1 or 0. In the modern version, it is not just bits, but qubits, quantum bits of information, that give rise to the fabric of the cosmos. The correlations among qubits may weave space-time itself, with gravity emerging as a large-scale echo of their entanglement. Hints of this connection appear in black hole thermodynamics. The entropy of a black hole, proportional to the area of its event horizon, suggests that geometry encodes information. The temperature of Hawking radiation, the evaporation of black holes through quantum effects, suggests that space-time itself behaves thermodynamically. These clues point to a hidden unity between gravity and quantum mechanics, a unity not visible in their separate equations, but revealed in their overlap. The fact that black holes can be described both by Einstein's curvature and by quantum entanglement implies that gravity may be the shadow of quantum information. Research in ADS-CFT strengthens this picture. In this duality, a gravitational theory in a curved spacetime is exactly equivalent to a quantum theory without gravity on its boundary. The geometry of spacetime emerges from the correlations of quantum fields at the edge. Entanglement, in particular, plays a crucial role. Studies show that the connectivity of spacetime, whether two regions are joined by a wormhole or separated entirely, depends on patterns of entanglement. In this way, gravity and geometry appear not as inputs, but as outputs of quantum information. To imagine the universe this way is to invert our hierarchy of understanding. We tend to think of spacetime as fundamental, with quantum particles moving within it. But perhaps the particles and their entanglement are the true foundation, and spacetime is the emergent stage they construct. In this vision, gravity is not an independent force, but a byproduct of entanglement, the thermodynamic effect of quantum correlations at large scales. This perspective carries extraordinary consequences. If gravity emerges from entanglement, then unifying relativity and quantum mechanics is not a matter of forcing them into a single framework. It is a matter of realizing they were never separate at all. Relativity describes the emergent geometry. Quantum mechanics describes the entanglement that generates it. The two are not rivals, but partners, each a reflection of the same underlying reality. The thought is breathtaking. It suggests that every step we take under gravity, every orbit of every planet, every curve of starlight across the sky is not the action of a force, but the echo of entanglement playing out beneath the surface. The familiar pull we feel is not fundamental, but emergent, a reminder that reality's deepest code is quantum information. To connect gravity to the quantum is not merely to solve a technical puzzle. It is to glimpse the hidden unity of the universe. Entanglement may be the deepest clue we have that gravity is not fundamental, but emergent. Imagine spacetime as a vast network where every point is linked to others by quantum correlations. The strength and pattern of these links determine whether two regions of spacetime are near or far, connected or separated. Geometry is no longer an independent backdrop, but the large-scale map of entanglement itself. In this vision, distances and curves are not given, they emerge from the quantum code. Researchers exploring ADS-CFT have uncovered striking hints of this. In the duality, the entanglement entropy of a region in the boundary theory corresponds to the area of a surface in the bulk geometry. This is known as the Ryu-Takayanagi relation, and it suggests that geometry arises directly from entanglement. If the entanglement pattern changes, the geometry changes. In this sense, space-time itself is elastic, not because of mass or force, but because of quantum information. Gravity, then, is the manifestation of how entanglement shapes geometry at large scales. Black hole thermodynamics offers another clue. The laws of black holes mirror the laws of thermodynamics in uncanny ways. Their entropy is proportional to area, their temperature defined by surface gravity, their energy by mass. These parallels are not coincidences. They hint that space-time behaves like a thermodynamic system, that its geometry is the emergent average of microscopic degrees of freedom. In this picture, a black hole is not just a gravitational object, but a thermodynamic engine, where information, entropy, and entanglement define its properties. The evaporation of a black hole through Hawking radiation becomes not a puzzle, but a process of information flowing back into the universe. The "it from qubit" idea crystallizes this vision. If the fabric of reality is woven from qubits, then gravity is not an additional force layered on top of quantum mechanics. It is the natural thermodynamic result of entanglement among those qubits. Einstein's field equations, describing how mass and energy curve spacetime, may be nothing more than emergent relations, like the laws of fluid dynamics describing the flow of water. They are powerful and precise, but not fundamental. They arise from the collective behavior of deeper constituents. This perspective does not diminish gravity, it elevates it into something even more mysterious. It suggests that every orbit, every wave of light bent by a star, every ripple of space-time from colliding black holes is a visible echo of invisible entanglement. What we perceive as geometry is the shadow of information. What we perceive as force is the thermodynamic flow of entropy. Reality, at its core, is not made of particles in space-time, but of information that creates both particles and space-time. If this is true, then the unification of physics comes not from bending quantum mechanics to fit relativity or forcing relativity into quantum form. It comes from recognizing that both are emergent, both are approximate languages describing the deeper code of entanglement. Quantum theory reveals the rules of that code. Relativity describes the large-scale picture it produces. Together, they point toward a unity where gravity is no longer fundamental, but a consequence. No longer a rival to quantum mechanics, but its child. This shift is radical, but it may be the only path forward. For nearly a century, physicists have struggled to quantize gravity, to fit it into the mold of the other forces. Every attempt has collapsed into infinities and contradictions. Perhaps the problem is not with our mathematics, but with our assumptions. Perhaps gravity resists quantization because it is not fundamental. Perhaps we have been chasing a mirage when the true foundation lies in information. And so the quantum connection may be the key. It may reveal that the most universal of forces is not a force at all, but the thermodynamic reflection of entanglement. It may show us that the weight we feel and the space we inhabit are illusions born from quantum data. It may tell us that reality itself is computation, and that gravity is the proof written across the sky. Gravity's connection to the quantum world forces us to reconsider what we mean by reality. If space-time itself is emergent, then the bedrock of existence is not distance, not duration, not curvature, but information. This is the heart of the "it from qubit" vision, that what we call the universe is a tapestry woven from entanglement, with gravity as its most visible thread. To live within such a universe is to live inside a projection, a structure that only seems continuous and solid because the underlying code is hidden from our senses. Black holes remind us most vividly of this hidden structure. Their entropy scales with surface area, not volume, as though their true essence is encoded on a boundary. Their temperature reveals that spacetime can radiate like a thermodynamic system. Their evaporation forces us to confront the fate of information, challenging our deepest assumptions. Every clue points to the same conclusion. Space-time is not fundamental. It is emergent, and if space-time is emergent, then so is gravity. This insight reframes the great failure of modern physics, the inability to merge relativity and quantum mechanics. Perhaps they do not merge because they were never separate. Relativity is the emergent description of geometry. Quantum mechanics is the description of entanglement. One describes the stage as it appears, the other the code that builds the stage. Together, they are two perspectives on the same reality. The clash between them is not a contradiction, but a misunderstanding of their roles. Consider what this means for unification. For decades, physicists have dreamed of a theory of everything, a single framework uniting all forces and particles. The strong, weak, and electromagnetic forces are already united within the quantum framework. Gravity resists, standing apart. But if gravity is emergent, then it was never meant to be unified in the same way. It belongs not alongside the other forces, but above them, as a statistical phenomenon arising from their deeper interactions. In this light, unification is not about squeezing gravity into the quantum mold, but about recognizing it as the large-scale consequence of quantum rules. This is why the study of entanglement has become central to the frontier of physics. Researchers simulate networks of qubits, watching how geometry can emerge from patterns of correlation. They explore dualities like ADS-CFT, where spacetime is built from quantum theory on a boundary. They investigate the thermodynamics of black holes, searching for the hidden laws of information. Piece by piece, they are assembling a picture where gravity is not a fundamental force, but the thermodynamic face of quantum entanglement. The implications ripple outward into philosophy. If reality is emergent, then the solidity of the world is an illusion. If gravity is the shadow of information, then every experience we have is shaped by patterns hidden beneath the surface. The cosmos becomes not a machine of particles, but a computation of qubits, a story written in entanglement. Our place in it shifts as well. We are not merely creatures moving through space-time. We are participants in the unfolding of information, bound to the same rules that weave galaxies and bend light. And yet this view does not diminish the wonder of the universe. It amplifies it. To know that every orbit and every fall is the echo of entanglement is to see the cosmos as even more intricate and mysterious. To walk under gravity is to feel the pull of information itself. To look at the stars is to glimpse the emergent geometry of hidden qubits. The quantum connection does not solve every puzzle, but it opens a door. Through it, we see that the most familiar force is not what it seems. Gravity is not fundamental. It is the shadow of something deeper, the thermodynamic trace of entanglement, the whisper of information shaping reality. Every bold theory must face not only the test of observation, but also the scrutiny of its peers. Emergent gravity, daring in its scope and seductive in its elegance, has inspired excitement in some quarters and skepticism in many others. Physicists are trained to be cautious, to trust evidence over imagination, and to demand that new ideas match the precision of established frameworks. For all its promise, emergent gravity has not yet reached that standard. Its critics are many, and their challenges cut to the core of the proposal. The first challenge is observational. Dark matter, despite remaining invisible, explains an extraordinary range of data. From galaxy rotation to gravitational lensing, from the cosmic microwave background to the growth of large-scale structure, the dark matter model has proven astonishingly successful. Emergent gravity, by contrast, reproduces some galactic dynamics, but falters at larger scales. The bullet cluster, where visible matter and gravitational lensing are displaced from one another, stands as a powerful example. Dark matter explains it naturally. The particles pass through each other while gas collides and lags behind. Emergent gravity struggles, for it must explain the same separation without invoking hidden mass. For many physicists, this single observation is enough to raise deep doubts. The second challenge is predictive power. Dark matter theories make clear, testable predictions. They describe how structure should form, how galaxies should cluster, how the microwave background should appear. These predictions are borne out with striking accuracy. Emergent gravity, in its current form, has not yet delivered such comprehensive predictions. It provides elegant insights and intriguing fits to certain data, but it lacks the detailed framework to match the breadth of dark matter models. Critics argue that until emergent gravity can rival this precision, it remains an interesting speculation rather than a competing paradigm. The third challenge is theoretical. While Verlinde's proposal connects gravity to entropy and information, it does not yet specify the microscopic degrees of freedom that produce these effects. In thermodynamics, we know that heat and pressure emerge from molecules. In emergent gravity, what are the molecules? What is the underlying structure of information? Without a concrete foundation, critics argue, the theory risks being an analogy stretched too far. It gestures toward a deeper reality without providing the machinery to build it. Yet, even as critics point to these weaknesses, they acknowledge the value of the attempt. Science thrives on ideas that challenge orthodoxy, even if they fail. Emergent gravity forces us to question assumptions, to ask whether dark matter is truly a substance or a sign of misunderstood law. It pushes us to connect gravity, entropy, and information in ways that may illuminate new paths. Even if it collapses under the weight of evidence, it will have sharpened the questions, guiding us closer to the truth. This tension between enthusiasm and skepticism is the lifeblood of physics. Bold ideas must be tested, challenged, and refined. They must endure criticism and survive confrontation with data. Many will fall. A few will rise. Emergent gravity now stands in this crucible, facing critics who demand not elegance, but accuracy, not analogy, but evidence. Its fate will depend on whether it can rise to that demand. But history reminds us that every revolution in science has faced resistance. When Copernicus placed the sun at the center, many dismissed the idea as absurd. When Einstein proposed relativity, some ridiculed it as philosophy disguised as physics. New frameworks always appear incomplete, always stumble in their early tests, always meet with skepticism. Emergent gravity may be no different. It may stumble now but grow stronger as its foundations are clarified and its predictions refined. Or it may fade, remembered as a bold but flawed step along the path to something greater. The critics are not enemies, but essential allies. Their skepticism ensures that only the strongest ideas survive. Their challenges push emergent gravity to confront its weaknesses, to sharpen its predictions, to seek evidence with clarity. In this struggle, science advances, not by avoiding criticism, but by embracing it. Emergent gravity is no exception. Whether it endures or falls, its critics ensure that the truth, whatever it may be, will emerge clearer in the end. Criticism of emergent gravity does not come only from observation, but also from theory. Many physicists question whether Verlinde's proposal has a sufficiently rigorous foundation. They argue that while the analogy between gravity and entropy is compelling, it risks being too general. Thermodynamic reasoning can reproduce many features of physics, but without a clear microscopic description, the analogy may mask gaps rather than fill them. For emergent gravity to move from speculation to accepted framework, it must provide the detailed architecture of the information that underlies space-time. Without that foundation, critics say, the theory is elegant but empty. Another line of skepticism points to the successes of general relativity itself. Einstein's equations have been tested in countless ways and have passed each test with extraordinary precision. From the orbit of Mercury to the detection of gravitational waves, relativity's predictions have been confirmed again and again. Emergent gravity must reduce to Einstein's equations in all these domains, while also explaining galactic rotation without dark matter. That is a delicate balance. Any deviation from relativity must be subtle enough to escape detection in the solar system, but strong enough to explain cosmic anomalies. Critics argue that achieving this balance may be impossible. There is also resistance from the human side of science, the inertia of established paradigms. Dark matter has dominated cosmology for nearly a century. Generations of scientists have built careers on its study. Entire experimental infrastructures are devoted to its detection. To suggest that it may not exist at all, that emergent gravity could render it unnecessary, threatens not just equations, but institutions. Such shifts are always met with resistance, for science is not practiced in isolation, but by communities invested in particular visions of the cosmos. Critics may be cautious, not only because of evidence, but because of the weight of tradition. Yet the sharpness of criticism is also a sign of vitality. Ideas that do not matter are ignored. Emergent gravity is not ignored. It provokes debate, challenges assumptions, and forces defenders of dark matter to sharpen their arguments. Even its critics often concede that it illuminates the deep connections between gravity, entropy, and information. In this way, emergent gravity serves as both theory and provocation, reminding physics that its foundations are not finished, that even the most familiar force may conceal secrets. The challenges remain immense. Emergent gravity must match the full power of the dark matter paradigm, from lensing in clusters to fluctuations in the cosmic microwave background. It must provide a clear microscopic description of the information that builds space-time. It must survive not only criticism, but precision. Until then, it remains a bold idea, hovering between promise and speculation. Its critics ensure that it will not advance without evidence, and in doing so, they safeguard the integrity of science itself. The story of emergent gravity would be incomplete without acknowledging the strongest doubts. Perhaps the most persistent critique is that the theory explains too little. While it offers intriguing matches to galaxy rotation curves, it does not yet reproduce the vast suite of successes that dark matter accounts for with apparent ease. The clustering of galaxies across cosmic scales, the delicate ripples in the cosmic microwave background, the dynamics of galaxy collisions, these are triumphs of the dark matter paradigm. Emergent gravity, in its current form, lacks the mathematical depth to tackle them all. Critics argue that until it can stand shoulder to shoulder with dark matter in every test, it cannot be considered a serious alternative. Another criticism is practical. Dark matter is a flexible hypothesis. It fits into the existing framework of particle physics, extending rather than replacing our standard models. It motivates experiments, guides observations, and yields testable predictions. Emergent gravity, by contrast, demands a paradigm shift. It asks us to abandon the notion of gravity as a fundamental force and to rebuild our picture of space-time from information and entropy. This is a far more radical step, and it comes without the same level of predictive infrastructure. Critics say that while radical ideas can be valuable, they must offer more than philosophy. They must yield tools as useful as those of the paradigm they seek to replace. There is also the problem of clarity. In physics, successful theories describe not just what happens, but why. They specify the constituents of reality and the laws that govern them. In thermodynamics, we know heat emerges from molecules in motion. In emergent gravity, the deeper components remain undefined. What are the qubits, the fundamental degrees of freedom that generate space-time? How do they interact? Without clear answers, some critics see emergent gravity as evocative but unfinished, more poetry than physics. And yet, even these doubts reveal the theory's value. By pressing against its weaknesses, critics help refine the questions that matter most. If emergent gravity cannot explain the bullet cluster, why not? If it cannot fit the microwave background, what does that reveal about the true role of dark matter? If its microscopic foundation is unclear, what paths of research could illuminate it? In this way, the criticisms are not roadblocks but signposts, guiding both supporters and skeptics toward deeper truths. History teaches us that revolutions in physics are rarely neat. Einstein's relativity faced resistance, quantum mechanics was doubted for decades, and the expanding universe was once dismissed as fantasy. Some bold ideas collapsed, others reshaped science forever. Emergent gravity now walks this uncertain path. It may falter under the weight of evidence, remembered as a daring but flawed attempt. Or it may evolve, strengthened by criticism, into the foundation of a new physics. No one can say for certain. What is clear is that the debate itself is vital. Emergent gravity challenges the complacency of assuming that dark matter must exist simply because it is convenient. It forces physicists to consider whether gravity, the most familiar of forces, might be an illusion. And in doing so, it sharpens the very science that may one day prove it wrong. Whether it stands or falls, emergent gravity ensures that physics remains alive, restless, and unwilling to accept mystery without question. That is the true measure of progress. And in this sense, even its critics must concede that the theory has already succeeded. Imagine a future where the debate is over, where the evidence has spoken with clarity, and emergent gravity stands not as a speculation, but as the accepted framework of physics. The implications of such a triumph would be staggering. It would mean that gravity, the most familiar of all forces, is not fundamental. It would mean that space-time itself, the stage upon which all cosmic drama unfolds, is not bedrock, but tapestry, woven from information and entanglement. If emergent gravity wins, it will rewrite not just physics, but our understanding of reality itself. The first victory would be unification. For more than a century, physicists have struggled to reconcile the smooth geometry of Einstein's relativity with the grainy probabilities of quantum mechanics. The two frameworks refuse to merge, but if gravity is emergent, the problem dissolves. Relativity is revealed as the thermodynamic description of spacetime, an emergent approximation of deeper rules. Quantum mechanics, in turn, describes the entanglement that generates those rules. The clash between them was never a contradiction, but a misunderstanding of their roles. Emergent gravity would show that the dream of unification lies not in forcing them together, but in recognizing them as two sides of the same coin. The second victory would be cosmological. Dark matter and dark energy, which together dominate the universe in the Standard Model, would be reinterpreted as illusions born of emergence. The missing mass and the accelerating expansion would not require invisible substances, but would arise naturally from the thermodynamic structure of space-time. The cosmos would no longer be a dark universe filled mostly with unknowns. It would be a luminous universe where information and entropy drive the motions of galaxies and the growth of structure. The mysteries of dark matter and dark energy, which have haunted astronomy for decades, would dissolve into clarity. The third victory would be philosophical. If gravity is emergent, then reality is not what it seems. The solidity of space-time, the pull of gravity, the very notion of distance and duration would all be revealed as emergent properties of hidden information. We would live not in a fundamental geometry, but in a construct, a hologram woven from entanglement. The universe would be understood not as a machine of particles in space-time, but as a computation of qubits, a story written in information. The implications for philosophy, metaphysics, and even consciousness would be profound. The scientific revolution would ripple outward. Textbooks would be rewritten. Entire fields of research would shift. The search for dark matter particles would end, replaced by the search for the microscopic degrees of freedom that build space-time. Gravitational physics would no longer be about forces and fields, but about entropy and information. Cosmology would no longer invoke invisible substances, but emergent laws. The very language of physics would change, from mass and force to entanglement and entropy. If emergent gravity wins, it will not erase the past, but build upon it. Newton's laws will remain accurate for falling apples and orbiting moons. Einstein's relativity will remain precise for black holes and gravitational waves. but both will be seen as approximations, emergent descriptions of a deeper order. Just as classical mechanics is an approximation of quantum theory, relativity will be recognized as an approximation of information theory. The history of physics will be reframed as a sequence of revelations, each showing that what we thought was fundamental was in fact emergent. And perhaps most importantly, if emergent gravity wins, it will open the door to new horizons. For if gravity and space-time are emergent, then what else might be? Perhaps matter itself, particles and forces, may also be emergent from information. Perhaps the entire universe is not built from substances, but from patterns, from rules that generate reality, the way simple equations generate fractals. In such a vision, physics becomes the study not of forces and fields, but of computation, the decoding of the hidden algorithm that creates the cosmos. To imagine this future is to feel both wonder and vertigo, the force that binds galaxies, the geometry that shapes the universe, the stage upon which all existence unfolds would no longer be primary. They would be shadows, illusions, emergent properties of something deeper. And in piercing the illusion, we would glimpse the true architecture of reality. If emergent gravity were to prevail, the shift would not be confined to the ivory towers of physics. Its victory would ripple through every corner of human thought, forcing us to reconsider the meaning of reality itself. For centuries, gravity has been our most immediate connection to the cosmos. It grounds us to the earth, shapes the path of the moon, drives the tides, and carves the fates of stars. To be told that this familiar force is not fundamental but emergent would be to realize that even our most intimate experience of nature is an illusion. Such revelations change not only science but culture, reshaping how humanity imagines its place in the universe. The search for dark matter would end in silence. The vast detectors buried beneath mountains and oceans, built to catch particles that never came, would stand as monuments to an old paradigm. Their failure would not be a loss, but a lesson, proof that the universe does not yield its secrets to brute force alone, that sometimes we must change the questions instead of the instruments. The funds and energies once devoted to finding ghostly particles would flow instead into probing the fabric of space-time itself, into studying entanglement and entropy, into deciphering the hidden code of information that shapes reality. Cosmology would enter a new golden age. Freed from the assumption of invisible matter and mysterious energy, scientists would seek to map the entropic laws that drive the universe's structure and expansion. Surveys of galaxies would not be aimed at weighing unseen mass, but at tracing the patterns of information that govern cosmic growth. Gravitational lensing would become a probe not of hidden particles, but of emergent rules. Even the cosmic microwave background, that ancient light, would be reinterpreted not as a fingerprint of dark matter, but as a fossil record of information shaping geometry in the universe's infancy. The philosophical consequences would be no less profound. If space-time is emergent, then the cosmos itself is a story written in hidden code. The question, what is real, would no longer have the same meaning. Distance, time, and gravity would be emergent illusions. Beneath them lies a deeper order, unseen yet fundamental. For philosophers, this would echo old debates about the nature of reality, from Plato's shadows on the cave wall to Descartes' skepticism about appearances. Emergent gravity would show that modern physics had arrived at a similar conclusion, armed not with speculation, but with data and equations. Reality itself would be revealed as a projection. This victory would also open new avenues for technology. If information and entanglement are the foundations of reality, then studying them more deeply could yield tools beyond imagination. Just as the understanding of electromagnetism gave rise to radio, light bulbs, and the digital age, the understanding of emergent space-time could give rise to technologies we cannot yet conceive. Perhaps we might manipulate space-time directly, engineering gravitational effects, not through mass, but through information. Perhaps the control of entanglement could unlock new realms of communication and computation, bridging distances in ways that seem impossible today. In education, the story of physics would be retold. Children would learn of Newton's apple and Einstein's curved space-time, but they would also learn that these were steps on the way to a deeper truth, that gravity is emergent from information. Just as we now teach that heat is not a fluid but molecular motion, future generations would learn that gravity is not a fundamental force, but a statistical effect. They would grow up knowing that the universe is not built from matter and space, but from information and entanglement. What seems radical to us would be their common sense. The triumph of emergent gravity would remind us that science is not a finished book, but a living story. Every victory rewrites the past, reframes the present, and reshapes the future. If emergent gravity wins, it will not only transform physics, but transform our sense of existence itself. We will know that the pull we feel, the stage we inhabit, the very flow of time we trust, are emergent illusions. And in that knowledge, we will glimpse the deeper code from which reality is written. If emergent gravity were to claim victory, the transformation of science would not end with gravity alone. Once one pillar of physics is revealed to be emergent, suspicion naturally falls upon the others. If space-time itself is woven from entanglement, then what of matter? What of the particles and forces that form the standard model of physics? Could they too be emergent, not fundamental, but byproducts of deeper informational rules? The triumph of emergent gravity would not just rewrite one chapter of physics. It would open the possibility that the entire book must be rewritten. This is the gateway to unification. For decades, scientists have dreamed of a single framework that unites all forces of nature. The Standard Model unites electromagnetism with the weak and strong nuclear forces. Gravity, stubborn and elusive, has remained outside. Emergent gravity would turn the quest on its head. It would show that gravity does not need to be forced into the quantum mold, because it is not fundamental at all. It would suggest instead that everything we see, particles, fields, forces, and space-time itself, emerges from one hidden layer of information. In this view, the long-sought theory of everything is not a larger equation, but a deeper code. Philosophy would wrestle with the consequences. If reality is emergent, then what does it mean to exist? Are we inhabitants of a fundamental world, or are we patterns in a computation? Are we objects, or are we stories written in entanglement? Such questions, once confined to speculation, would take on new urgency in the light of science. The boundary between physics and philosophy would blur, as it has in every great revolution, from Copernicus to Einstein. Emergent gravity would force humanity to ask again the oldest of questions: what is real? The cultural impact would be equally profound. Just as relativity transformed our language with the ideas of curved spacetime and time dilation, emergent gravity would reshape our metaphors. We would speak of information as fabric, of entanglement as thread, of reality as a tapestry. Artists, writers, and thinkers would find inspiration in the idea that existence itself is emergent, that the universe is a projection of hidden order. The story of gravity would become not just science but mythology, a tale of illusion pierced by human curiosity. In such a future, even the way we look at the night sky would change. No longer would we see stars as suspended in the void, bound by the invisible glue of dark matter. We would see them as patterns in a grand computation, their motions the visible echo of entropy. No longer would we see the universe as dominated by dark unknowns. We would see it as luminous, governed by emergent law. The cosmos would appear not as a puzzle of missing pieces, but as a masterpiece of hidden design. The triumph of emergent gravity would not end mystery. It would deepen it. For if gravity and space-time are emergent, then we must ask what lies beneath them. What is the true nature of the information that builds reality? What rules govern its flow? Where do the qubits live, and what breathes life into their correlations? These questions would become the new frontiers, the challenges of the next century of physics. Emergent gravity would not close the book but open it wider, revealing vistas we can barely imagine. If emergent gravity wins, humanity will have achieved one of its greatest feats. We will have taken the most universal of forces, the most familiar of experiences, and revealed it as an illusion. We will have pierced the veil of reality itself, glimpsing the hidden code that writes the cosmos. The apple that once fell for Newton and the stars that once curved for Einstein will be recognized not as signs of a fundamental force, but as shadows of information. And in that recognition, we will know that science has carried us one step closer to the deepest truth of all. The story of gravity is the story of our expanding vision of the cosmos. Once it was an invisible tether, a mysterious action at a distance that bound the apple to the earth and the earth to the sun. Newton gave it form through law, showing that the same force guiding falling fruit steered the motions of planets. For centuries, that vision reigned. Then Einstein arrived, revealing that gravity is not a force at all, but the geometry of space-time, bent by mass and energy. With him came the image of a universe where space and time are dynamic, flexible, alive. Now, at the edge of the 21st century and beyond, a new vision rises. Gravity, it whispers, is not fundamental even as geometry. It is emergent, born from information, entropy, and entanglement. The future of gravity will be decided by evidence. The next generation of telescopes, surveys, and detectors will carry the weight of this decision. They will map galaxies in exquisite detail, trace the bending of light with unmatched precision, and listen to the faintest ripples of space-time. They will search not just for hidden matter, but for hidden rules, the subtle fingerprints of emergence. If emergent gravity is correct, these instruments will reveal deviations from the dark matter paradigm, anomalies that cannot be explained by invisible particles, but fit naturally into the language of entropy and information. If emergent gravity fails, the silence of evidence will deepen the mystery, and the search for dark matter will continue with renewed urgency. But the future is not only about testing, it is about imagination. If space-time and gravity are emergent, then physics itself must be reimagined. The next generation of theorists will not only write equations of curvature, but also equations of information. They will study entanglement as architects study blueprints, knowing that the patterns they find may build the universe itself. They will treat gravity not as an isolated puzzle, but as a window into a deeper order where forces, fields, and geometry all emerge from the same hidden code. This shift will not erase Newton or Einstein. It will embrace them, showing that their visions were not wrong but incomplete, approximations of a deeper story. Newton's laws will remain the language of falling apples, Einstein's equations the language of black holes and gravitational waves. But behind them, like the invisible loom weaving a tapestry, lies the code of information. To understand gravity's future is to see these frameworks as steps on a staircase leading us toward the ultimate architecture of reality. Philosophy will follow close behind. If gravity is emergent, then reality itself is not what it seems. Space and time, weight and motion, all dissolve into shadows of entanglement. What we call real may be projection. What we call fundamental may be illusion. This does not cheapen reality, but enriches it, revealing that the universe is deeper and stranger than our senses can grasp. It forces us to ask not only how gravity works, but what it means for something to exist. The future of gravity is also the future of humanity's curiosity. For every time we have reimagined this force, we have also reimagined ourselves. When Newton showed that the same law governed earth and heavens, humanity learned that it was not separate from the cosmos, but part of it. When Einstein showed that space and time bend, humanity learned that reality itself is malleable. If emergent gravity proves true, humanity will learn that even the most universal force is not fundamental, that we live in a universe woven from hidden code. It will remind us that our understanding is never final, that every law we write may be an echo of something deeper. And so the story continues. From Newton to Einstein to Verlinde and beyond, gravity has guided our imagination as surely as it guides the stars. Its future lies not in certainty, but in exploration, in the relentless pursuit of evidence and the courage to question even the most familiar truths. Whether gravity remains geometry or is revealed as emergence, its study will carry us closer to the heart of reality. For in the end, the future of gravity is the future of physics itself. If gravity is emergent, then everything we know, space-time, matter, energy, is only the beginning. The true story of the cosmos lies beneath, in the invisible architecture of information. To discover it will be to rewrite not only physics, but reality. And perhaps, when that day comes, we will look back at the centuries of falling apples and bending starlight and realize that they were all clues, signs pointing us toward the greatest revelation of all. That gravity, the force we thought we knew, was never a force at all, but the most magnificent illusion of the universe. The future of gravity will unfold in the laboratories and observatories of the coming decades. Vast arrays of telescopes will peer deeper into the sky, charting the dance of galaxies with unprecedented accuracy. They will map gravitational lensing across the cosmic web, searching for patterns that betray the fingerprints of emergence rather than particles. Gravitational wave observatories, more sensitive than today's instruments, will listen to the universe with new ears, capturing not only the thunder of colliding black holes, but the whispers of space-time itself. If gravity is emergent, somewhere in those whispers will lie the telltale signs, subtle deviations from Einstein's perfect equations that reveal the hidden code beneath. At the same time, quantum laboratories on Earth will probe the microcosm for connections to the macrocosm. Entangled qubits will be manipulated and measured in ways that mimic the structure of space-time. Quantum simulators may one day recreate in miniature the emergence of geometry itself. In these experiments, the line between physics and philosophy will blur. Researchers will not simply measure forces and particles. They will watch reality emerge from information. They will glimpse, however faintly, the architecture that builds the cosmos. The educational revolution will follow. Future generations may grow up with a very different picture of the universe than ours. For them, gravity may never be taught as a fundamental force, but as an emergent effect. Newton's apple and Einstein's space-time will be milestones on the road to information theory, not endpoints. Students will learn that the universe is not built from mass and energy, but from patterns of entanglement. That space and time are not givens, but illusions. That reality itself is woven from information. What now feels radical will one day be common sense. Philosophers, theologians, and artists will also grapple with the implications. If gravity and space-time are emergent, then existence itself is revealed as something stranger than matter moving in a void. It is computation, pattern, code. Are we then participants in a cosmic algorithm, players in a simulation written in qubits? Or does the word simulation miss the point, for the rules of emergence may be reality itself? These questions will fuel debates not only in lecture halls but in literature, film, and culture. The future of gravity will be the future of how humanity imagines its place in the cosmos. But no matter how far our imagination runs, the future of gravity will always be tethered to evidence. That is the essence of science. Theories rise, not because they are elegant, but because the universe affirms them. Emergent gravity must win its place, not in the pages of philosophy, but in the light of data. The orbit of stars, the bending of light, the shape of the microwave background, the ripples of space-time. These are the judges that will decide gravity's fate. Their verdict will come slowly, piece by piece, as new generations of scientists measure the cosmos with greater precision. And yet, whatever the verdict, the pursuit itself is transformative. To ask whether gravity is emergent is to stretch our imagination to its limits. To test that question is to sharpen our tools, refine our theories, and expand our vision. Even if emergent gravity fails, the attempt to prove it will have deepened our understanding of relativity, dark matter, dark energy, and the quantum world. Even failure would be progress, for science advances as much through what it disproves as through what it confirms. Still, we cannot help but wonder, what if it succeeds? What if the data points not to invisible matter, but to hidden law? What if the pull that holds us to the Earth and binds galaxies together is not a fundamental force, but the thermodynamic whisper of information? What if space-time itself is a projection, a grand hologram written in qubits? If that future arrives, then gravity will not only have been rewritten, reality itself will have been revealed anew. The closing chapter of gravity's story, at least as we can glimpse it today, is not an ending, but a horizon. From Newton's apple to Einstein's space-time to Verlinde's emergent law, each vision has deepened our understanding and transformed our place in the cosmos. The future will bring either confirmation of emergence or confirmation of dark matter, or perhaps something stranger still that none of us yet imagine. What matters is not the outcome but the journey, the relentless drive to question even the most familiar truths, to test them against the light of stars and the ripples of space-time, to never accept mystery without curiosity. If emergent gravity proves true, then the force we thought we knew will be revealed as illusion. The pull of the Earth, the orbits of planets, the arcs of galaxies, all will be reinterpreted as shadows of information. The cosmos will no longer be a dark universe dominated by unseen matter and energy, but a luminous one governed by emergent law. The mystery of gravity will dissolve not into particles, but into patterns, not into substance, but into code. And we, fragile beings bound by curiosity, will know that even the most intimate of forces is not fundamental. It is emergent, an echo of something deeper. If emergent gravity fails, then its failure will still have enriched us. It will have forced us to sharpen our tests of dark matter, to refine our models of cosmology, to deepen our exploration of the quantum world. It will remind us that bold ideas, even when wrong, drive science forward. It will stand in the lineage of great speculations, like phlogiston or the ether, that illuminated the path even as they were left behind. Science thrives on risk, and the risk of emergence, whether won or lost, ensures that physics remains alive and restless. But whether it stands or falls, emergent gravity leaves us with a profound gift, the reminder that reality may not be what it seems. To walk under gravity, to feel its pull, is to live inside a story that may be written by information itself. To gaze at the stars is to witness not just matter in motion, but the emergent geometry of hidden entanglement. To exist is to participate in the unfolding of a code that we are only beginning to glimpse. The future of gravity is therefore the future of reality, for to rewrite gravity is to rewrite the very stage upon which all existence unfolds. And so, as we close this exploration, we return to the simplest of questions. What is gravity? Newton saw a force. Einstein saw geometry. Verlinde and others see emergence. The truth, whatever it may be, awaits us in the light of evidence. But one thing is certain. If gravity is emergent, then the most familiar of forces is only an echo of something deeper. And to rewrite gravity will be to rewrite reality itself.